Good morning. Good morning. Bishop, can you hear me? Go.
Okay, so I'm going to share my screen one more time. Okay.
Sorry? Yeah, I am.
Yeah. Yeah, this one here, right? This one, this one. Okay, cool. Yeah, the video is focused in right. Is it focused? Yeah, I'm on. That video camera? I zoomed in a little bit. There's autofocus. Okay, because I think that was this camera. So we replaced the camera now. Okay. The sound's okay? Okay, cool. Yes. Yep. Morning, everyone. So welcome back to day 2 of the ArduPilot Developer Conference in Kaga. If you check out the local newspaper, we're front page of one of them and maybe second or third page of the other one. So congratulations, everyone. And yeah, special thanks, to all those great demos we saw yesterday. I think no one will ever forget the parachute drop, the heavy lift, the VTOL. I mean, Leonard's fast rover. Anyway, so many great demonstrations yesterday. Okay, so on the screen here is today's schedule. It's pretty much the same as yesterday. We have a couple more talks, but we also have a little more time. First speaker is Andy Piper.
Thanks. Let me reshare. All right, just feel the energy in the room. Okay, so I'm going to talk about fast rate loops, or perhaps more precisely, fast rate loops, but that's a little bit of a mouthful. Oh. Aha. Okay, quick overview of the agenda. So I'm going to talk a little bit about control principles. I defer to the experts in the room. So I'm sort of, if they say something that contradicts me, believe them, not me. But I'll give you my sort of simple view of the world, which has stood me in good stead for the way I've sort of run and flown copters in particular. And then talk about rate control in particular and how you can get good rate control in copters. A little bit about requests versus outputs, and then a digression into what makes Betaflight so good for acro, effectively, and how we're sort of starting to compare with them, or even do compare with them. A little bit on the limits of rate control, like what stops us being perfect, and then the implementation that I've done. So there's a PR for this that I was flying yesterday. So the demo you saw was flying this code, which was a little bit scary, but it all worked out well. And some of the challenges I ran into producing that, and then some results, some sort of numbers-based results, and then what I might do in the future. All right, moving swiftly on. A little bit about me. So I work for FOSS UAV, but really that's just me. That's my side hustle company. My day job is that I run the engineering department for an AI startup based in Oxford. And that consumes a bunch of my time, and then this consumes the rest of my time, and I sort of have no time for anything else. But this is my passion, is drones and flying and coding to some degree. My background is actually in sort of big systems, big enterprise systems, distributed systems, primarily in Java. But early on in my career, I did C++, which is why I'm sort of now hacking once again. on ArduPilot. All right, so control principles. There's not really to sort of give you a 101 on control principles, but just to emphasize that the controllers that we use, that are PID controllers, proportional, integral, derivative, are based on, I don't know whether, my cursor doesn't work, are based on the error. Okay, so it's just really important to remember that these controllers are based on reacting to error. And so you sort of want you to hold that in your mind as we sort of go through this. So we detect an error, we apply some sort of proportional input based on the error, integral based on the error, derivative based on the error, create new outputs, and then go around that loop again. So it's a feedback process. So just talking about error a little bit more. So where does the error come from? And there's essentially two places. So one is reacting to your stick inputs, essentially, or the EKF controlling the vehicle or whatever. So this is control input. And the interesting thing about this is it's slower. So on copter, radio maybe hits 200 hertz tops. And I think on plane often it's 50 hertz. So just sort of relatively low update rate. And you put in a control input that makes a rate request. Then you have an error between what you requested and what's actually going on. And so the copter adjusts. And we do that pretty well. But then you've got to think about disturbance error. So this is, so I've got a little copter here. So it's not the one that was flying yesterday, but it's almost identical. So disturbance error is where something hits it externally, usually prop wash or noise or whatever. And what you got to remember with this is that can happen at a very, very fast rate. So if you sort of fly through prop wash, you've got to, just very, very, very fast rate of error being created. And we adjust for that quickly at the moment. We adjust for that in the main loop at 400 hertz. Okay. So diving in a little bit more, so typical sort of PID response type graphs might look something like this. So you can see in the blue we've got a step input here, and we've got different responses to this based on the different parameters that would be set for P, I, and D. So you can see on the red we've got a very damped response here. Sort of it gets slowly to the target. You can see the purple overshoots by a massive amount and oscillates, gradually damping down. The one I haven't shown here is where the copter flies away, and that's where the oscillation keeps building up and to infinity. And then the green one is sort of roughly what we want, which is a sharp response followed by meeting the required target. And I've shown this graph before, but there's a little bit of an error in this graph that is relevant to this talk. And you see what I did there. So the error is that there's a little bit of latency between the step response and actually creating the output. So it would be more it would be more correct to show the step response occurring earlier, and then the step input occurring earlier, and then the rate response occurring a little bit later with a little bit of latency. And it turns out this latency is actually very, very important to good control, at least for micropters. So if latency is important, how do we manage latency in control? And the thing we've just looked at is sort of feedback latency. So something happens, you react to it, you produce an output, and that minimizes the error buildup. So what you got to think about is you got a copter like this, and a disturbance comes in, and you've measured where the copter is, and what the error is between what you want and what you need. What you got to remember is the copter keeps moving after that measurement has happened until you apply the output, and so you get this error buildup that is very much dependent on the latency between reading and reacting. And so this is latency that you want to minimize to get more accurate control. There are other things you can do. So you can actually do feed forward input. And so this copter does feed forward and derivative feed forward. And this is where you sort of got a model where you can predict what the output will be based on an input. And therefore you don't have to wait for the error to build up. You apply the output directly. And that works for some situations, but you can't sort of know exactly what's going to happen. You can't control a copter that way, although planes are obviously controlled much more based on feed forward. But it is important. And so in particular for these sort of copters, derivative feed forward as well allows you to sort of snap into and out of rolls, for instance, where you're moving your sticks very, very quickly. You can use derivative feed forward to get that kind of very fine stopping and starting. So it's useful in some places. Okay, so the other bit about optimal rate control is the tune, and that's in a whole other talk. And I'm not really going to talk about that. I'm not going to talk about that. But there are things like you got to be able to detect the error very precisely. So you got to have fast, accurate, stable sensors. You got to have good filtering. It's got to be low lag filtering. You got to get rid of noise. You got to have a good frame. You got to have motors that work well. Lots and lots and lots of stuff. You get any one of these wrong, and the rate tune can be messed up to some degree. And obviously, you're trying to push the thing. So a very stable tune is not necessarily the most responsive tune. So you're sort of playing around with how close you can get to that sort of runaway oscillation that gives you good response without sort of crashing in the corners, as it were. So whole other talk, as I said. So relevant to the implementation I've done is just thinking about the request, the rate request. So the rates are these are rotational rates. So you're making a request for a rotational rate of the copter. And there's kind of two parts from that. There's the target, which is coming from your control inputs, and which you can apply feed forward to, can be noise free, and it can also be run more slowly. Okay, so this is the point about the control inputs being slow. Your fingers just can't move that quickly. You can run the control input component of the rate request more slowly and still get the response you're looking for. Whereas the target error correction, you have to run really, really fast because you just have no control over that. You're reacting to disturbances. Has lots of noise in which you're also reacting to. And so the faster you can run there, the more you can minimize that latency, the better control that you can get. So a little bit about why Betaflight is so good, but I would say ArduPilot is pretty comparable now if you do things right. And a lot of this is to do with rate control and how we've sort of optimized rate control. So obviously I've sort of missed out Leonard's whole kind of life's work of the control systems, which I take as a given here. But on top of that, obviously we had notch filtering in 4.0, which was a big improvement in terms of how we were managing noise for these sort of very fast responses. Then we pushed up the filtering rate for sensors in 4.1, which allows us to sort of address sort of aliasing issues. Again, it's sort of a noise reduction mechanism. And then also in 4.1, we had BD shot, which allows you to provide very precise control to the motors and get feedback very precisely. So you can sort of target the noise very precisely. Betaflight does all of this. And then in 4.5, derivative feed forward was introduced. And people have started to begin to use that, and it just allows you to get this sort of very sort of snappy response that people are looking for, and also PID notch filtering that Bill mentioned yesterday. So Betaflight does all of these. The thing that Betaflight does that we don't do is running the rate control loops much faster than we currently do, and this is kind of the thesis of my talk. It's a good thing. There's a PR. Hopefully we'll get into the code base at some point in the near future. And I think with that, we're pretty close. I mean, it's difficult, maybe there's some sort of little edges and stuff, but this high frequency rate control is the sort of last major piece that was separating what Betaflight could do in essentially in sort of acro flying conditions versus what we could do. So this should now say, why is ArduPilot so good, I guess. Okay, so what are the limits to rate control? So I've talked a little bit about latency. And one of the things to remember is latency is sort of a cumulative effect. So it's not just like latency of calculating the rate outputs. You want this whole other pile of things that couple together. So you can see on the left-hand side, so we're going to read the sensor, and this is happening in an SPI thread. We're then going to apply the filters, the notch filter, and then pass on that data to a calculation for the rate outputs that we response, which involves a handoff currently to the main loop, which is also a thread. We then push the calculated outputs to the motors, where there is another thread handoff to the D-shot thread, which then makes the actual output to the motor, which then goes to the ESC. So the ESC then has to calculate what it's going to do, spin up the motor, the props turn, and eventually that control output that you're looking for based on your read of the error happens. And it's just this long chain of pieces. And what we want to do is try and squash that down as much as possible. And so what I've kind of put sort of red and green here. So the SPI thread, D-shot thread, ESCs, those are all happening pretty quickly at the moment. The piece that's happening more slowly is this rate control calculation, because it's happening in the main thread. And people push the scheduled loop rate up to sort of address this issue, but it's very much constrained currently by things like GCS updates and all that sort of stuff. So, people have gone up to maybe 1 kilohertz tops, but after that, you start running into all sorts of problems. Okay, so we basically want to run the rate loops fast to reduce latency. So how do we do that? So as I've sort of demonstrated, what we want to do is minimize the latency from gyro read to the motor output. Now, one of the things we've done in this sort of in this new PR is rely on the sensor stability. So rather than measuring when we get, when we actually read samples, what we're relying on is the gyro to produce samples very regularly and rely on the timing of those samples to drive the rest of the process. So we're kind of making that assumption that the gyros are reading at a very regular basis, and that we can use that timing to drive everything else. And if we make that assumption, we can then have a little queue of gyro samples that we keep in a ring buffer, and we just basically process those serially. So it almost doesn't matter when we process them, but in the ideal scenario, we're basically reading a sample when it's available, which should be roughly at the rate that the gyro is producing them. So, depends on how you sort of configure things, but say 4 kilohertz. Now, those samples, we have to process all of them for all the things we currently do, things like filtering and so on. But for the rate thread and rate control, we actually only care about the last one, right? Everything that's historical before the one we've currently got is pretty much irrelevant. It's just the last one that we can that we care about. And we can use that property to control the speed of the rate thread. So we can actually skip samples sort of evenly to make the rate thread go faster or slower, depending on sort of our CPU constraints. And that works pretty well. And so this is all happening so skipping samples is happening in the SPI thread as we read the samples. And then we have a separate new thread, rate thread, that is dequeuing those samples, applying the rate calculation, and then outputting to the motor. And ideally, what we want to do is do that for every sample. So we basically want this step, step, step. Question from Leonard.
Just a clarification, when you're talking about skipping samples, we're talking about skipping samples after those samples have been passed through the filters.
Correct.
Yeah.
Yeah, so the ETF still sees everything. Yeah.
So the low pass filter, the band,
Yes.
they're not so processed on every sample.
Yeah.
But it's post all that filtering is where we're skipping the sample.
Yeah, 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 absolutely. Okay, so, and what we essentially want to do is run this in lockstep if we can. So read a sample, filter, calculate the rates, output to the motors, boom, 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 for each sample, if possible. So there's some challenges with that. So this is going quite fast now, and there's a lot going on in ArduPilot. Lots of other processes, threads competing for CPU, and this is a 10x, speed improvement, for instance, from what we're currently doing. So default scheduled main loop rate is 400 hertz. So what I'm trying to do here is run the rate outputs at 4 kilohertz. So we've got 10 times the processing going on. And that means everything in that hot path suddenly becomes quite expensive. At the most, we've got 250 microseconds for each of those ticks to do stuff. And there's no way we can consume all of that 250 microseconds to process rate requests because there's so much other stuff going on. We've got to leave plenty of spare cycles for the rest of the vehicle to behave appropriately. The other thing you've got to remember is that essentially we're processing 10 gyro samples for every main loop update. And the main loop also has a view of gyro samples. So the start of the main loop, it gets a published view of what's going on in the gyros. And it retains that published view through all of the processing that subsequently happens. Meanwhile, the rate thread is doing 10 updates. And there's a danger, and I sort of saw this in testing, that you essentially get time travel where the rate thread and the main thread are dealing with different samples that can be in different points in time. And we want to avoid that, right? We want to have consistency between the main thread's view of the world and the rate thread's view of the world. And then a final challenge is logging. So we want to make sure that the logging is consistent as well, which means for rate-related things, we want that to be output from the rate thread, not from the main thread. Because so one of the challenges here is that essentially the rate thread, because these things are happening concurrently, the main thread and the rate thread are happening concurrently, they just have a view of each other that is just changing all the time. And so we don't want to sort of lock those two together because that slows things down, but we just want to make sure that the views each has of the other is consistent at any point in time for the purposes that we want to use it for. All right, so if you use my PR, how do you set it up? So there's actually only 2 parameters, very easy to set up. Question from Tim. There's a mic there if you want to.
It's actually relevant to the previous slide, I think. It's always fascinated me that the 8743 has 2 cores. Could this rate thread run on the second core?
In theory, but yeah, there's some complexity involved there yeah. And really the complexity involved is the thing I've just described about the interaction between the main thread and the rate thread. So there's a lot of interaction going on there. If you separate that into 2 cores, it could still work, but you're just going to have to be super, super careful about those interactions happening in a consistent way. Yeah, that's true. It's true. Yeah. All right. So if you use my PR, how do you set it up? So there's only two parameters. So there's fast rate enable, which you basically set to 1. And if that's how you want to experiment with it, that's all you need to do. So that enables the rate thread, and it enables the rate thread with dynamic throttling. So I think one of the things you've got to realize about this is CPU is the constraint here. So even on an H7, CPU is the constraint here. And so I'm sort of trying to play with things to make sure that everything has enough CPU that the vehicle keeps flying. And so this fast rate enabled set to 1. It's basically throttling on this little queue of samples I talked about. So if you can imagine, Jira is producing samples, pushing them into a queue that gets dequeued by the rate thread. If that queue starts to grow, it basically means that the rate thread is not keeping up with the samples that are being produced. And so I use that information to throttle back the rate thread. It's sort of an indication that the vehicle is overloaded. And then I do a similar thing with the main loop. So the main loop has this ability to slow down and speed up based on vehicle load, and we can sort of read what's going on there. And if that's going on, then I can slow down the rate thread basically by skipping samples. So for instance, if I'm going reading samples at 4 kilohertz, and this is basically with a divider of 1. So for every sample producing an output, the next thing to do is have a divider of 2. So basically for every other sample produce an output and so on. And this is where this fast rate div parameter comes in. I've sort of not been able to find a sort of easier way of describing this. It works pretty well. People can get their heads around it. It sort of would make sense to describe this in hertz, but actually I found that to be more more trouble than it's worth. But if you've got a better idea of how to configure this, that would be great. So
this is just a decimation ratio.
Yes, correct.
Is the engineering term. So
Yes, agreed. There's an engineering term for it, so it must be simple. All right, so fast rate div you can set, and this will constrain the absolute speed that the rate thread will go at. So if you set this to 2, you will never get your rate thread running more than half of the gyro read rate, for instance. But this dynamic throttling can then happen from that fixed rate down. So you can always go slower than the speed implied by the fast rate div setting. And so this example I've just given, if you set it to 2, it divides the rate that the rate thread is running at by 2 relative to the gyro rate. There's 2 other settings. So there's 2, which basically means I'm confident, I feel lucky, which means that the rate thread output is fixed when you're armed. Then there's 3, which I tend to use for testing, which basically fixes it at all times. So you can kind of see the absolute CPU load that's going on. Because one of the things you find is there's certain operations that are quite expensive in Copter. For instance, the mag updates and the EKF is very, very expensive, and it's easy for that to kind of cause the rate thread to slow down and then speed up, slow down and then speed up, and that gets a little bit annoying if you're flying. And so if you're sort of confident that overall the vehicle is in good shape, then you can use this setting too. So that's the sort of user configurable piece. There's some implied configuration by these things. So there's this setting servo D-shot rate that people will have maybe come across. And this is a way of outputting in D-shot at multiples of the main loop rate. So by default, D-shot runs at a fixed 1 kilohertz. But if you set, for instance, servo D-shot rate to 2, you get D-shot output at twice the main loop rate. So 400 hertz main loop rate, 800 hertz D-shot, and so on. So you can sort of scale up how fast D-shot is happening. And the main reason to do that is because you want the feedback coming back from BD shot. So you want to get that fast frequency update. But the problem with that is you don't want to sort of you don't want to have D-shot rate set to, I don't know, 4, say, which would imply 1.6 kilohertz in normal circumstances. But 4 times 4 kilohertz gives 16 kilohertz. There's no way I want to run my motors at 16 kilohertz. So servo D-shot rate is implicitly adjusted to be essentially lower or equal to 4 kilohertz to make sure that doesn't get messed up. Similarly with the harmonic notch, there's a setting to do with running the harmonic notch at the main loop rate. So there's in INSH notch opts, you can set a setting and basically it will do the harmonic notch updates at the main loop rate. What we want is for that filtering to occur at the rate loop rate, but not necessarily running at full rate loop rate is not worth it too fast. So at the moment that's fixed to be half the rate loop rate. And then finally, logging is a great way of overwhelming this stuff. So trying to log at 4 kilohertz doesn't work. As you might imagine, the poor little SD card gets a bit upset. So the fast attitude logging is constrained to be at most 1 kilohertz, but never lower than the actual main loop rate. So that's the sort of implied setup. Okay, so troubleshooting. So what are the problems I ran into? So the main problem is CPU overload. This is where dynamic throttling is your friend. So you can start with dynamic throttling. There are GCS messages to tell you how fast you're going, whether it's speeding up, slowing down, and that gives you a feel for whether this is all just in Copter, by the way. There's only a Copter feature, not playing at the moment. And if you're not doing very well, if you need to get more CPU so you can run the rate loop faster, how do you do that? Well, there's a number of things you can do. One is to use fewer IMUs. So that reduces the CPU load from the sort of SPI threads. You can reduce the main loop rate. So this is one of the nice things about this change is once you start running the rate loop independently and fast, the need to run the main loop fast kind of goes away. So you can certainly don't need to run it more than 400 hertz, but you can actually probably lower it even more than that because it's only this rate loop reacting to error is the thing that needs to happen quickly. You obviously can increase fast rate div to slow down the loop rate. You can remove fast rate logging. And also you can reduce the overall gyro rate. That's another way of getting more CPU. So these are all ways of getting CPU if you're overloaded. Okay, so I have flown this. Well, you saw it flying yesterday, so it does work. What was the testing that I did? So basically I did testing with different fast rates. And there were 3 tests I ran. First was running SysID and running Bill's new spiffy tool that he'll describe later in the day. And I've got some graphs about that, so we'll look at those in a minute. But SysID basically oscillates the vehicle from very slow to quite fast. With these changes, you can actually get quite a fast oscillation. In fact, so fast you have to be a little bit careful that the copter doesn't climb away, but it's a good way of sort of seeing the physical response of the vehicle. I then also used this enable stats feature that is a way of looking at CPU load for individual threads. And then finally running auto tune for all of these different settings, because one of the things that you see with these changes is that basically you can get higher PIDs, so you can basically get higher responses for the vehicles. All right, so probably a little bit hard to see here, but this is Bill's tool. He will explain all later. But for my purposes, this is running on a SysID at. I feel like there's something being hidden on the right hand side here. I don't know whether we can. Yeah. All right. Move over here. Okay. So this first one is for. So what we're interested in is this 180-degree crossing point in the calculated rate. And you can see here that for 400 hertz, that's 20 hertz. And I'm sure Leonard can give a very technical overview of why we're looking at this. But basically, we want this to move to the right. So for 400 hertz, we've got 20 hertz here. And then at 1 kilohertz, you can see we've got 22 hertz. And then at 2 kilohertz, still a bit more than 22 hertz. And then 4 kilohertz, we've got 23 hertz. And so it's sort of a way of demonstrating that there is an actual improvement in the response of the vehicle using system ID. Now, these numbers may not seem like a lot, but they actually make quite a big difference to the overall tune, for instance. So, it's got really too small. So similarly, CPU load. So let me move this back over. So at 400 hertz, you can just about see that so I'm cheating a little bit here, but you can see this SPI1 thread is running at 4 kilohertz, and that's got 20% of the CPU. You can see there's 40% idle, and then the rate thread is taking 3.8% of the CPU. And if we go up to 800 hertz, you can see the SPI thread's roughly the same, 20%. Rate thread's now up to 7.4%, and idle is 32%. Go to 1 kilohertz, SPI thread still similar. The rate thread is now at 9%, idle 27%. 2 kilohertz. Okay, now we're getting into it. So SPI thread still the same. Rate thread is now consuming 20% of this, or 18% of the CPU, 16% idle. And then at 4 kilohertz, you can see there's only 7% idle. SPI thread is the same, and the rate thread is consuming 28% of the CPU. So you can see 8 kilohertz is probably beyond this copter at these rates. So this is the thing about running fast, is you can consume quite a lot of CPU quite quickly if you're not careful. But it does work, running at 4 kilohertz. There's still idle cycles left, which is great. And then in terms of the tune, so this is my tune at 400 hertz, and you can see that we've got quite high angle P's here, but the things to look at are the P values. So we've got 0.047 on roll, 0.085 on pitch. And then if we move to 2 kilohertz, we've got 0.072 on roll, 0.080 on pitch, and angle P values are still the same. And then 4 kilohertz, we've got 0.089 or 0.09 on roll and 0.131 on pitch. So if we compare that to the 400 hertz value, see it's getting on for about double. So the PIDs are roughly doubled, maybe a little bit less at 4 kilohertz versus 400 hertz. I should point out this is not the tune on this copter. This is on a different copter, which is much harder to tune. I probably should have done it on this copter. But even so, you sort of get, even on a copter that's got a lot of frame resonance and all the rest of it, you still get very good results from this. So, oh gosh, that's hard to see. Black on purple, there we go. All right, so the advantages of this: dramatically reduce latency from sensor read to motor output, which is the main sort of thrust that I've been talking about. There's some other advantages to do with PID filtering. So we do filtering in the PIDs. So if you think about Filt D and Filt E and Filt T, those are all running at much faster rates now. So 4 kilohertz, for instance, in this example. And so you get a higher Nyquist frequency, improved anti-aliasing. So there's some good sort of filtering benefits there. But the thing to note is really the improvements are most noticeable on small agile copters with responsive motors and ESC. So if you've got a big copter that moves only slowly, you're not going to see much benefit from this because it just can't physically react quickly enough to what it's being told to do. Whereas on a small copter like this, with very responsive motors and ESCs, it can react very, very quickly, and you do get this big, really quite big benefit. So future work. So we're having some discussions about how we can lower the FIFO read rates for the non-primary gyros, because one of the things you've got to remember about rate control is you really only care about the primary gyro. EKF cares about the others if you're going to have a lane switch, but as far as rate control is concerned, only the primary gyro and only the latest value that's come out of the sensor that is relevant. And if we do that, we can sort of reduce some of the CPU load from the unused sensors. We're sort of discussing making this the default in Copter at some point to remove some of the complexity. So at the moment you can sort of turn it on, turn it off, the thread starts, stops, all the rest of it. But if we made it the default, then some of the complexity in the code would go away. Not quite related to this, but the target updates could be done in sort of a more noise-free way, which I'm sure, again, Leonard can talk about if you're really interested. And then there's also the question is, we're only running the rate controllers fast. Should there be anything else that we run faster as well? Would that have any benefit? Difficult to know, but maybe. And that is it. These are my details. If sorry, Fossio V does consultancy on the side. I do, software development and all the rest of it. Please get in contact. And I've got a little YouTube channel which you can't see here, but I'm also hoping to do a few little sort of vignettes while in the conference. So if you're happy to be videoed, I'll come around with my camera. But thank you. Any questions? Question.
On the CPU load charts that you had up, how many IMUs were you sampling?
3. Yeah, but I was cheating because I was doing this lower FIFO read rates on the non-used ones. So
Have you run across Inspector Morse?
yes,
Seriously?
yes.
Wow. Okay, very cool.
Thinking about your sort of D and I terms in particular, have you thought about conversion between, because you're talking about trying to baking this in as a default. Any speculation as to, is it safe to just bump up the rates and D and I go, and you can say that your sort of temporal based parts of your controller are safe to run at a faster rate, but you could get more if you boost them. Is there any change, basically, is what I'm asking.
So I think if we made this the default would be the rates that you currently have just running in the new architecture, so 400 hertz. So, and I think on F4s, for instance, that's, I think you could probably, given what people try and do with F4s, I'm sure it's safe to go a bit faster than that, say 1 kilohertz for the rates, but whether any more than that, I don't know. But that's sort of the open question of what happens to all of those other controllers. At the moment, you can only compile this for F7 and H7. It basically compiled out. If you try and compile it, it won't compile for F4. But yeah, I mean, ultimately, it's sort of you don't have to run. There are some sort of latency benefits here anyway in the way the architecture works without running everything really fast. Pete?
So obviously, some flight controllers have multiple IMUs, and those IMUs might be running at quite different rates. So if you have a primary IMU switch, there could be quite a big change because you're just decimating the IMU samples that would change the rate at which your rate controller is running at. So how do we deal with that?
Well, so this happens already, right? So we get dynamics. If you do fast rate 1, you get dynamic switching of the rates in flight, and it's fine. So one answer might be, don't deal with that. Just sort of let it happen. If we decide that it is a problem, then we'll have to figure out how to sort of scale appropriately between them. But I've certainly in my testing, I've not, I've had it sort of going all over the place.
Mentioned that the rates, the backend rate changes, but it only happens, like we already discussed, it only happens like when you're trying to get the samples, right? Like we want to get one sample
which matches the backend rate hertz, but it only changes once.
Right, but I think isn't Pete's thing different because we're relying on the timing of the samples for this to work.
Right.
But I think you're saying if the timing of the
I
samples.
think Pete is saying that
differently.
if it changes between the IMUs, right? Like if one IMU is running at 2 kilohertz and the second IMU is running at 3 kilohertz, right? So you suddenly jump to the second IMU and you're completely changing the rates and stuff.
Yeah.
But if you were actually combining them and making them, in a sort of instead of 3 kilohertz, you're running at say 400 hertz, right? So you're already decimating it. So it's not that big of a deal. But if it is changing from 2 kilohertz to 3 kilohertz, you're completely changing the control, the gains that are required to tune the copter.
Yeah, I mean, one of the things I have noticed is, so if you stick with your original gains, then everything is safe. If you run at 4 kilohertz and then auto tune and dial everything up, if you then try and run more slowly, you can get a little bit more, the gains are then too hot for essentially the updates. So that's one thing you'd have to be certainly be careful about.
Also, you talked about actually dynamically changing the gyro rates. Are you also changing the rate of the rate control loop as well with that?
Yeah. So the rate thread is scaling up and down.
Right.
That's the thing that's changing.
So what's the impact of that on the whole, again, the gains and stuff that you have set? It's going to change, and it's also the time, the response of the frame itself is going to change based on how fast you are.
Yes. So certainly,
and your filters, notch filters, everything is going to sort of vary, right?
Well, yeah, I mean, the main thing is the impact of the gains, I think.
Right.
So I think the notch filters and so on will work fine.
Right.
But it's more of whether you've tuned it to the faster rates and then try and go slower. I think that's where the problem is. If you tuned it to the slower rates and then try and go faster, it's all fine.
I mean, it's still like and when we are slowing down, so you're slowing down by you're dividing by a factor, right? Like a 2 or something.
Mm-hmm.
And it's also a thing that you need to see that when we are running at 1000 kilohertz, when we say 1000, it's usually not 1000, it's more like 990 or 5 or something.
Yeah.
And when you divide it by 2, it's not going to be an exact harmonic as well. So it's
right.
And if you're really, really unlucky, it may sit right on the, on the resonance frequency of the frame and can cause other issues as well.
Yeah, I mean, I think generally, so the filters are always running at the higher rate, right?
Yeah.
So it's only the rate loop that's scaling up and down. So there's no change to the Nyquist for the filters or anything like that. It's simply, but there is a change, obviously.
But you are changing the control frequencies, though.
Yes.
Right. So, I mean, that can.
Yeah, but I mean, a lot of this is about higher is better, right? Running at. So
I think that's also another thing, like, is higher better or improving the latency better, right? So rather than running incredibly fast, what you want to do is reduce the time between the responses.
There's two, right? So there's the latency bit, but then there's also the fact that the filtering is happening at a higher rate, and so you're getting benefits there from the bit filtering.
Yeah. Anyways.
Yeah, I think the summary is it sounds to me that the summary is you just need to be careful when you're tuning and sort of tune for the worst case.
Yes, correct. Yes, which is kind of true.
Test everything carefully.
Yeah.
Right?
Tune for the worst case, but that's kind of that's good advice anyway, right?
I'll make a couple of points on this. The higher rate, the faster you're running the rate, your average latency is half your sample period, like half of the rate you're running. So that's if you're operating now and you're operating here, for half that time, you're actually operating on old data. Hang on, let me talk. So as you run faster, just the inherent fact that you're running at a higher frequency does give you the ability to tune sharper and because the effective latency is reducing. The fundamental latency at the beginning of that sample is always there, and the shorter we can reduce it, that just subtracts off everything, but it becomes a higher portion of your overall latency as you go to faster and faster update rates on your PID loops. So there is that. You do expect simply by increasing your update rate to see improved PID loop gains. And what everybody has said here about, you should really be tuning your aircraft up to the lowest expected update rate that you're going to see. And so, it would be fair to, if you can run at a decimation ratio of 2, to tune your aircraft at a decimation ratio of 4, and then turn it up to 2. And all that does is just give you a little bit more stability with that existing tune. So I think, there is that fundamental improvement expected from a higher update rate. Yeah.
I think you mentioned earlier on. Yeah, Randy here. So I think you mentioned earlier on in the talk that about the EKF's yaw update and how much time that takes, and it's variable. We don't update it every.
The mag fusion.
Yeah, exactly. The mag fusion for the yaw estimate. Is that totally resolved with this, or do we need to look through the code and find these bits of functionality that consume a whole bunch of CPU and try and throw them off into a separate thread so that they cause less problems, or is it resolved?
No, so it's not a threading issue. It's a pure CPU cost. So the mag fusion is basically just very, very expensive, and once it starts running, it sort of has to complete. And if you're trying to do lots of other stuff at the same time, it just takes a bit longer. That's the problem. So I think obviously it'd be nice to make that piece of code more efficient, but I don't know how we do that. Have to get Paul involved or something. So the approach I've taken is just to make this stuff as efficient as possible, so it doesn't impact the rest of what's going on. Any other questions?
So taking a step back and looking kind of more qualitatively at the flight feel of this, if you take a diehard beta flight pilot, hotshot pilot, and kind of give them before this PR, and have them fly against ArduPilot, like what kind of feedback do you get in terms of what they like and don't like? And then with this PR, like, do they say it feels identical, or do they still?
So I have a limited sample set.
Okay, if you're the hotshot pilot, then what's your feedback?
No. So I have a limited sample set that's not just me. So the reasonable beast flight pilots I've tested this on really like it. So say that it feels qualitatively different. In a sort of weird way, because you end up not getting this very jerky sort of response. It's a much smoother response, and yeah, certainly they are certainly able to notice the difference significantly. But of course, that all gets also into the feel of it, and there's a lot to do with how the input is shaped and all that sort of stuff that affects that response as well. But yeah, generally, I mean, I can certainly tell the difference when I'm flying, and I'm not a great pilot, but yeah, those who are certainly a lot better than me say it is great. And I think one of the things where you really notice it is in the corners where the copter's trying to do a lot. There's a lot of prop wash going on. There's a lot of disturbance. It's those sorts of situations where this works much better. Just sort of going flat out in a straight line, probably not going to notice not an awful lot of difference. Tridge.
Really great work, Andy.
Sorry, I should say Tridge started this work. Shout out to Tridge. Yeah.
I did. My implementation was pathetic compared to what you've done. So I think the one missing piece that might still be an opportunity to gain a little bit more latency is triggering the DMA for the D-shot output, because that's still happening in a separate thread, as I understand it, in the current PR. And I think we're going to have to find a mechanism for the rate thread to prompt the triggering of that DMA to happen immediately that the output is available, because I think that you've got some variable timing. The RC output thread is running at a priority 1 slot higher than your rate thread. But that's the same priority as the boost priority of the main thread, which means sometimes that main thread is going to be holding the CPU, and your RC output thread that needs to trigger that DMA is going to be held off for some indeterminate period of time. And I suspect you're losing 100 or 200 microseconds there sometimes. And if we could find a way to trigger that DMA immediately, you might find you get a little bit less jitter.
Yeah, no, I agree. And an example of this where it's really bad is where we're sharing DMA channels, and
Indeed.
and then you can get really very long delays. So yeah, I mean, it's sort of interesting. There's ideally what you want to do is schedule everything so it's sort of nothing's trying to happen at the same time, but obviously in a sort of multi-threaded situation, that's quite hard to achieve.
Particularly tricky when you've got other types of outputs on the same vehicle, like some servos and other things that are all being driven by the same RC output thread.
Yeah.
But if we can get that last little bit, I think you'll get a little bit more even output.
Yeah, yeah, agreed. No, good. All right. Thanks, everybody. One time. Thank you, Bill. Sorry, I should move out of the way.
All right, good morning. I'm Bill Geyer, back again, and this work is basically based off a lot of the work that I've done with Heli AutoTune. The idea behind Heli AutoTune was to get a frequency response and be able to predict kind of how far you can take the gains before you hit instability, and then kind of step into that tune in flight And so this takes it kind of one step further, but basically you can do it at your desk, so that you can basically find the frequency response of the bare airframe, come back to your desk, or do the flights, come back to your desk, and then be able to tune the aircraft at your desk, and then go out and fly the tuned gains, and then verify that what you've tuned is good. I've done this with a few different helicopters, one with a tandem, and then on some of my own. So so what I'm gonna do is I'm gonna step through my brief. First, I'm gonna kind of, for those that are not as familiar with time to frequency domain, I'm gonna kind of talk about the difference. Then I'll go into kind of what is a good tune in a frequency domain. What are you looking for when you're looking at this frequency response to say that, hey, I'm getting a better tune. And then I'll go into a little bit of theory behind the predictive capability of this tool and then I'll go into what the tool features are, and then give a little demo. So moving from time domain to frequency domain. So the multi-rotor auto tune kind of works in the time domain. It kind of does a twitch. It's looking for kind of the overshoot and the undershoot. And it's then kind of basically it's kind of looking at the free response, what we would call the free response of the system, to basically be able to then determine kind of what's the oscillatory nature of that free response, and then be able to then tune the gains on that. And so this takes it a step further, going into the frequency domain, and things that we're looking for to characterize the response in the frequency domain is what we call gain, which is basically the ratio of the output to the input in amplitude, and then also phase. And so we can see here our input is the blue, our output is the red, and we can see that the gain would be then just the magnitude of the output divided by the magnitude of the input. And we can put that in, a lot of times you'll see it in decibels, which is just a scaling for that. And then the phase is basically looking at, what's the phase between the peaks of the input and the output. And so here we're showing that here's the input, and typically your phase is going to be negative because the peak of the output is happening after the peak of the input. And so basically what we do is we look at this time between the peaks of the input and output, and then we can kind of quickly be able to determine, based on the period of the frequency, then be able to determine what that phase is. Again, like I said, most of the time you're going to be looking at negative phases. And if you see in your response that you're seeing positive phases, then there's something wrong. There's some problem with the data. So just be aware of that. So again, now kind of go into the idea of looking at the frequency response. What I've plotted here is basically a second order system, a simple system where basically we have see kind of well damped here, where it just comes down with the peak, and then kind of a more lightly damped mode where you have this peak here. And so again, that's kind of what we're looking for in the frequency response, to kind of tell whether we've got some areas where at that frequency, if you were to excite the system, you're going to see this overshoot. It's not going to stay with the input request. It's going to actually overshoot that input request. And so that's what this is indicative of when you look at your frequency responses. And real quick, for gain plot, when we show decibels, 1 to 1 is kind of what you want, and that's the 0 dB line. That's kind of what you want that to go out as far as you can before it drops off. You don't really want to go much above, because that means if you have it going above, then you're seeing some sort of overshoot in the response at that frequency. Right. So what defines a good tune? You want your attitudes to closely match the desired attitude. And we kind of look at that, you'll look at that in the time domain. You'll go into your log and you'll be like watching it, your log, to see how well does, that your actual attitude match the desired attitude, or your actual rate matches your desired rate. And that's kind of indicative of what that good tune is. And so the same idea here is you're looking for that on the gain plot, you're looking for that line to kind of go along go along 0 dB, which is basically a 1 to 1, meaning that your output is equal to your input request. And you really don't want to have any type of increase in that gain as you go out to higher frequencies. And so basically, I kind of drew this in there. It's a little shaky, but basically you want a good tune is really indicated by your gain plot going out as far as possible along the 0 dB line. And then at some point it is going to drop off, and that's okay. But you're looking to see that drop off as far out in frequency as you can within the capabilities of the aircraft, right? And the aircraft's going to dictate that. And then your phase, you generally want your phase to drop off as well, but you want to see that it doesn't drop off too quickly. Filters and other things that's like that are going to cause that could cause a lot of phase delay or cause this to drop off quicker. So you're really try to minimize how quickly that phase drops off out at the higher frequencies. So that's the basic idea behind in the frequency domain. What do you want to see? How do you want that to look in order to dictate a good tune? So a little bit about the theory behind this. Like I said, I've really been working to try to look at, hey, are there better ways that we can, figure out how well we can tune a vehicle and optimize that tune, or at least be able to do that in an easier fashion rather than going out and doing multiple frequency sweeps or multiple twitches and continuously doing that, taking 5, 10 minutes of flight time to really tune the aircraft, when you can just basically go and do one sweep, come back, kind of fiddle with it at your desktop, and then go back out and fly and be confident that you're going to have a good tune. So basically it goes along this theory where we're assuming that the aircraft is a linear system. What does that mean? Well, it basically means that we don't have any discontinuities or nonlinear kind of effects where we have either rate or acceleration limits. Those will affect our linearity. We're assuming that the tune, like our gains, aren't changing over time. So if you're using something like what is that, the SR, the slew rate limiter type thing, that would be bad, because if it comes into play, then that's going to change the gains over time. So you really want to make sure that your system is basically staying consistent with the gains as you're doing this frequency sweep and as you're looking at this tune. So what this does is then it goes, the first part of the analysis is determining the bare airframe response, right? What does that mean? Well, that's basically, the bare airframe response is basically, you take the input to the motors class and you look at the output response from the aircraft and you figure out what that transfer function is, or what that frequency response is. And that's what we call your open loop transfer function, right? That's the open loop frequency response of just the basic airframe without any control wrapped around it. And then what we do in the math is we wrap the loops. We basically apply all the control laws analytically, right? We basically wrap these loops analytically, and it's done through, Laplace transform. Really, we're doing Fourier transform type math that we're looking at this in. I'm showing it Laplace transform, kind of Laplace domain here. But basically, the closed loop response is basically looking for the response of the aircraft. This response divided by with respect to the input from the pilot or whatever's making the inputs to the system. And so that's our closed loop response. This math here basically is the math that basically goes and does that, working on the frequency response data that's in a complex form, complex number form. So here's the control law diagram. Basically, I had to go through the code and figure out, thanks to Amilcar, I think he wrote did the control law diagram there and helped out with that. I think you had as well, Leonard. But basically, using the control law diagram, making sure I understand kind of where all the filters are and where they're making inputs in, what data they're pulling in. And so this is basically a representation as a wired diagram of the control laws for the attitude controller. And you can see here's the aircraft, the open loop response of the bare airframe. And then this is the measured rate, which Leonard gives that to us through the sysid mode as the unchanged GY, GX, and GZ, which is the gyro rates. And then we can apply the filters in the INS gyro, the notch filters, and then feed this back into the different rate and attitude controller. And then we're applying the low pass filter here, applying the error notch filter here. Here's our PID transfer function. So that's all the rate. That's the rate PIDs that's contained in here. We have the target filter for the low pass, target notch filter. And then we have our attitude feedback where we compare it to the desired attitude or the target, and that gives the correction rate to the rate controller. And up here we have the feed forward path for the rate controller as well. So this is the basic control law diagram for our attitude controller, and basically this, or actually equations then now are the equations that define that I use to calculate the transfer function or the frequency response for the rate controller, and then for the attitude controller down here. Questions? Okay. All right. So how to use it? You're going to go out and you're going to do a frequency response, or you're going to go out and do a system ID mode flight. And you'll most likely want to use because we have a lot of shaping with the SysID axes 1, 2, and 3. Those are like the pilot input axes. There's a lot of shaping there that could affect, like you have these rate limits and acceleration limits. Those could affect the results. So you probably don't want to use those. If you have to, that's fine. You probably won't be able to compare some of the calculated to the predicted, because if those limiters kind of come in, that would affect the results of the calculated. But in any case, you want to use SID axes 4, 5, or 6, which is for the roll, pitch, and yaw, which we call recovery roll, which basically doesn't have the feed forward enabled. And then you'll have that data. One note here is that make sure you do all your filtering ahead of time, because the filters will affect the response. So make sure you go ahead of time and get your filtering in there for the INS gyro and the notch filters in there on the gyro signals. So get those filters completed, and so your control signals show very low noise. In most cases, the SID or system ID logging rate of 100 Hertz is fine. It's mostly what I've used in all of my stuff, maybe for Andy where he's running the fast rate loop. Probably 400 Hertz is probably going to be more applicable. But remember, the logging rate is set for the system ID. The logging rate is set for using the log bit mask, fast attitude, medium attitude selections there, and the combinations of that give you different rates. That's the SID magnitude. You don't need large magnitudes for the oscillation. Less than 5 degrees is plenty. I typically use 5 degrees. Sometimes I'll back it off to 3 degrees if my tune isn't as good and I'm seeing a lot of the aircraft overshooting a lot. You can back that off. Again, as I note there, if you see the oscillation starting to grow more than 10 to 15 degrees, stop the system ID, retune, try to get a little bit better tune to keep the aircraft from getting too large of response. The concern there is that it continues, and all of a sudden now the aircraft goes unstable and you crash. So if you see things starting to grow and it gets scary, stop the system ID, come back out of it, try to retune a little bit better, and go on from there. Again, big warning, you want to have a stable initial tune, and the big thing that's going to probably creep up and could hurt you is basically those low frequency modes. So what we consider the long-term or the phugoid mode type is basically what's going to be probably your biggest nemesis in trying to do this. So trying to make sure that's stable so you don't get any type of large oscillations is going to be good. All right, so tune the tool. So it is published and out there online. And so the first thing you do is just basically start by loading a log file from your system ID flight. And you choose your file. As far as the FFT window, 1024 is a good for 100 hertz. You could go a little higher if you're looking at 400 hertz data. But I found 1024 works well for 100 hertz data. Next, once you've loaded the data in, you can then choose your axis that that your SysID mode was conducted in, and then you can select the time, the start time and the end time. So one thing about this is that thanks to Andy Piper for a little bit of help that he gave me, thanks to Pete Hall for all his help in this web tool. But Andy was able to set it so the web tool only looked at the start and end time of the system ID run. Well, in this case, you can see that I had 3 system ID runs, and so it took the start and end time of all 3 of those, which in between I went, turned off system ID and did it another time. The tool right now will only work for a continuous system ID, right? If you have an area where you weren't in system ID and you were maybe in stabilize or another mode, then it's going to cause problems with the tool. And the reason being is that some of the parameters or some of the signals it's looking at when they're not in system ID mode are sampled at a different rate. And so all your signals need to be sampled at the same rate, and that's why we only look at data that's in the system ID mode. And so now I've selected one of my system ID runs, and so I've got that set. And at this point now, I hit the calculate button down here at the bottom left-hand corner, and that will do the initial calculation of all the frequency responses based off of the actual data. Here's the INS settings. These will be loaded in automatically when you load your log file. The INS settings for that system ID run. So they have the 2-notch filters. They have the INS gyro sample rate and filter, low pass filter there. And then we have the loop rate is up here for the loop rate, and then we have the attitude control parameters for that axis that you're trying to tune. Over here on the right is the notch filter, the PID notch filters. Right now we don't have any selected, but if you select one of them, and you can add those in, right? Maybe you didn't have PID notch filters, but you can add that in with the parameter settings, and then quickly add that in and be able to look at how that affects the tune. So what I show here in each of the plots, so this is the plots you'll see, and it shows basically the gain plot in the top, or amplitude in decibels. It shows the phase plot in degrees. It doesn't wrap well, so you'll see it goes from -180 to +180. That's one of the future improvements we want to do, is try to get that wrapping to work. And then down at the bottom is most important is the coherence. Coherence speaks to the goodness of how well the output correlated to the input, right? Anything below 0.6 is generally not trustable. Above 0.6 is good. More closer to 1 is even better. But so, in this case here, you probably can go from maybe 2 or 0.2 hertz to maybe 8 or 8.5 hertz. So, that's the important thing here is I show all the data. You want to basically make sure that what you're looking at and what you're using to tune has good coherence. And so for the predicted value, I use the bare airframe coherence. So you have a reference of what the bare airframe coherence is, because that's what the prediction is based on. And so that's put in there so you kind of have a reference as what your prediction was based on. So there's different selections at the bottom, and I'll go to the tool here in a minute. So here's the bare airframe response. I believe this is a multi-rotor. So you see that here, yeah, 90 degrees phase. You can see there's a little bit of wrapping here, but acceleration command system for bare airframe of a multi-rotor. And again, this is what the algorithm's using to predict the closed loop responses. And here's the parameters that it's using to generate these transfer functions or these frequency responses. So again, remember that all the calculated lines here are based off of actual data. It's going into your system ID flight and grabbing the data at the different points in the control laws to give a comparative frequency response that would be equivalent to the frequency response that predicting for the rate loop, for the attitude control loop. So for the rate controller, here's what the parameters we're picking for the calculated responses for X, Y, and Z, or for pitch, roll, and yaw. And then here's the comparison. Again, this compares initially what you're getting based on the parameters. So it should compare well. When you do this, you should see a good comparison between what you ran and what was predicted. If you don't, then there could be some nonlinearities in the system. Maybe you had some acceleration limits or something about your system, your aircraft has some nonlinearities to it. So just be cautious. That's a good way. This is a good way to check to make sure that you have a good prediction. Controller shown, and so here's the parameters it uses to do the calculated frequency responses for attitude controller. And again, there's the predicted stuff, and you can see it compares really well. And then finally, input shaping, right? So this is now going from what the pilot's going to make as far as an input, or the ArduPilot, and then looking at the frequency response of what the response is to the pilot's inputs. And this includes those for the attitude controller, includes the input shaping or the input TC, input time constant, right? So that's why you see this roll off here of so here's our attitude controller loop, here's the input shaping. You can see it kind of rolls it off because that's the input shaping of the input TC causing that. All right, so let's go ahead and look at an example here. Hold on a second. Let's see here. I have it. There it is. Okay, so I loaded up. This is a tandem heli that I recently helped provide a little better tuning on. And so it's just for the pitch axis. The user was complaining about there was like a low frequency oscillation going on and needed help with the tuning. So I had them do a frequency sweep, and I took the data, loaded it, hit calculate, and then it loads all the parameters, and then I get my initial frequency responses for the rate controller compared to the calculated ones. And so we can see in the response here, you can see a little bit of a rise. You can see it's like almost a 5 dB rise, which means it's like almost a 2 times, the overshoot was almost twice of what the requested input was in the rate response. And then we kind of see back down here, it goes back to 1 or 0 dB, but then we see a little bit of a rise out at maybe 7 or 8 hertz, which is essentially one of the modes of the aircraft, kind of a lightly damped mode of the aircraft that we want to try to control better. And so initially what I had to do was and kind of what I'm looking at now is just the gain plot. I said, well, I want to get rid of this low frequency oscillation. So because it's a tandem rotor helicopter and it's a pitch axis, it acts more like it behaves more like a multi-rotor, right? Because you have these two rotors that are commanding differential thrust. And so basically I said, well, that's probably because it's more of a feed forward thing. So if we bring down the feed forward, right, to reduce that, and at some point you saw that the feed forward, it doesn't change the response anymore, kind of went down. So I got down to about oops, I went the wrong way. There we go. So reduce this down, and we can see that now it's starting to flatten out around 1. I can keep it there, and now I can start bringing up my my D gain if I want to bring up the D gain to see how much I can bring that up. It's at 0.006 now. And so it automatically starts calculating immediately. And you can see the peak isn't getting any larger, but I have to be careful out here because I'm really close to where my data has poor coherence. So I kind of have to be careful about how far I push this out or maybe go get additional data. But let's go ahead and bring up the P gain. That'll help hopefully flatten things out. So as I bring up the P gain, you can see this is all kind of now flattening out along the 0 dB, except for when I get out here, I start seeing now again the this almost 10 dB. No, I'm sorry, like a 6 dB rise. So it's like 3 or 4 times overshoot. So at this point, now I can start, I can introduce a, what I found with helicopters is that you could reduce these lightly damped modes out at these high frequencies by basically just adding a notch on the target. And so if I add a notch on the target, I can now put that notch in here. I just have to put in the parameters. There's the same parameters that you're seeing when you put them into the actual mission planner. So filter type 1, now my notch frequency, I look down here, see it's around 7-ish hertz. So I can put 7 in there. And so there you go. You see it kind of immediately put this, you can see the notch taking effect. 40 dB for helicopters. That's what I went back and talked about yesterday, that, really what I'm just trying to do is kind of take the rise off of there, kind of shape it so it just flattens it. And so I don't need 40 dB. I can get away with maybe, let's look at 8. Still a little bit too much. How about 5? Yeah, so I'm starting to flatten it out a little bit. I can take and maybe widen the notch. It'll make me 1.5. And that kind of widens things out. And kind of now, at least now I don't have that peak there, which means I don't no longer have that overshooting that's going to happen at that frequency. If I get hit by a gust, or if I'm making inputs, I'm not going to see the aircraft responding by overshooting a lot. So again, I can now take that and look at, and so here's the different selections down at the bottom for the control loop. So I can look at the attitude controller at that point and see what I got. You can see I get a nice flat line going along 0 dB or 1-to-1 as it rolls off. And then I can even look at the image shaping that I might have on this. And then that shows kind of what the pilot's going to see from their perspective when they make inputs to the system. I think that's all I got. Questions?
So a question about your workflow then, typically, in terms of, because you've got a predicted step, what do you do in terms of your like pre-post? How do you then, once you go flight test again, what kind of things are you looking for to try and see that what you've done predicted previously now is matching reality once you've applied the changes and tested?
Yeah, so if you go out and run the frequency sweep again, when you come in and load it, your gains will all load up as what you had in the aircraft. And so you're looking at, that the predicted matches the calculated. And that's kind of your verification that, hey, the changes I made are actually good and everything matches well. I mean, so they should match exactly, very close to what you it should match. Yeah, it should match very close.
Very interesting. How happy are you with the abstraction and transplantation of the actual controller versus the replica you have here that predicts the new response?
I'm very satisfied that. So as with everything, take it with a grain of salt. You're going to go, I would not suggest that you just immediately go out to the new gains. I mean, you got to be careful if you don't understand entirely what's happening here, right? This is more designed for folks that have some understanding of frequency response. flight. And frequency response testing and kind of playing and doing this type of analysis. You know, you can't just go and say, well, I'm going to just drive up the D gain and maybe the peak is actually off of your chart. You have to be very, I would take incremental steps, you know, look at something, make some inputs or make some changes, then go out, fly it, do a frequency response, get the CIS ID, get more data, kind of make sure it matches, and then just kind of step yourself into your new tune.
Yeah, your mileage may vary, of course. My question is more like from the standpoint of someone who has tried to make mathematical representations of the actual code we have in the code base. How easy did you find to do this abstraction from the code base to the tool you have here?
Yeah, I mean, so it wasn't, bear in mind, you have to kind of, I've been working with Leonard for a number of years now, so I understand the code base fairly well. There are the nonlinearities are what you have to be worried about. I mean, yeah, you kind of have to know where the rate limiters and the acceleration limiters kind of rear their ugly heads. And so that you can, and basically, like I said, that is not included in this representation. That's outside. It's really difficult to do as far as predicting that kind of stuff. Again, we're looking at a linear system, so you got to keep your amplitude small and the rate small, so that basically you stay within that linear response.
Excellent, thanks.
Just on that point, within the code, would it be possible if we were to start logging just some flag of some description when we start tripping over some of those limits? Oh, I've just been told by Leonard we do. Okay, so maybe we could, as a next step, we could just start putting some warning flags in this tool, just so it takes a little bit of the guesswork out of how are we tripping into that non.
Yeah, no, and that would help, you know, verify that if you're seeing some differences between the predicted and calculated as to, oh, well, yeah, potentially I've got some, I see in the log that I hit some rate limiters or acceleration limits. So yeah, then you kind of know.
Yeah, I sent a cryptic message to you on Skype too, and we may be able to do things like look at our rate limits and adjust the magnitude throughout that sweep as we get to the higher frequencies to keep us from hitting the rate limits. Because it's quite deterministic. There's a question on Zoom. Can you get stability margins from this tool? Do you have plans to add this? If not,
yes, there is the possibility to rework the frequency response, or to rework the transfer function to do what we call the broken loop, kind of a broken loop transfer function that would then be able to then identify what your stability margins would be. I think I took a stab at it, and I hadn't fully worked it out yet. The other thing you could do is you could go and provide a transfer function that would predict the disturbance rejection bandwidth or the disturbance rejection frequency response. And so that would then, you could then go in there and kind of look at how your disturbance rejection compares to what you'd and tune that.
One of the reasons why I prefer having the graph wrapped the way you've got it up here is you can clearly see where it crosses the 180 degree point. And
well, and there's a selection down here. I kind of left it in there, but the unwrap, you can select between wrap and unwrap. You can select between linear, as far as the scaling of the gain between linear and dB. And you know, Pete Hall had done all this work up front, so he made it super easy for me to basically be able to glom onto what he did and be able to make use of this graph and really have a powerful tool. Any other questions? In the back.
I mean, I would just say thanks very much for adding an excellent web tool, and I really hope this is sort of the future of tuning ArduPilot. Hopefully we can, or I'd like to in the future, we'll add tool tips and make it a little bit more user friendly like some of the other tools, and try and get some documentation and things. Because I know or if you're not familiar with this stuff, this is quite overwhelming. The sort of first time is certainly,
Yeah.
it's
And that's
taken me
why
a
I
long
caution
time.
people to, you know, be careful in using it, you know, take baby steps, when you're looking at tuning things. Yeah. So, and I ultimately, you know, Leonard and I have talked about this, hoping somebody comes along, or maybe if I feel that, that I can really do that, is to actually have a separate thread that would run in auto tune that basically would do this, you know, what I'm looking at and doing graphically, that it does it in auto tune. And then basically you do one sweep at auto tune, runs a thread, does the calculations, and then comes back with a new set of gains. You do a second sweep, it verifies that you're done. But again, that's a lot of work to take what you look and hear and then, you know, figure out how you're going to change gains. It's a
Thank you very much. Brief clarification. Apologies if my understanding is a bit layman on this, but you mentioned the criticality of having your INS and your notch filters established prior to going into this tool, but then you showed early on a couple dialog boxes where you were kind of evaluating those. So does this give you the capability to evaluate the quality of your filtering as well, or is it really absolutely critical that that's perfect going in?
It's not. So the big thing about filtering is just making sure that you don't have that your noise levels in your control signals are not such that it's limiting your tune capability. It's going to show you. It will show filter, you know, possible gains of filtering, you know, that a better filtering, or maybe you've filtered too much and it's going to show that you've you know, you've got a lot more phase loss because you have too much filtering at the INS level, right? So yeah, that would, you certainly could use it to kind of evaluate your filtering, but only in the control band. You know, notice that I don't have I'm not getting good frequency response out at where like my notch filters for helis are at like 20 hertz, right? For the rotor modes. So I'm not out at that point. I'm only looking at the control, kind of the control frequencies. So again, yeah, I don't have good, well, I didn't do the frequency response out that high, but yeah, I don't know that you'd get good, good coherence all the way out to those high frequencies. So certainly you could tell how it affects your control range of frequencies. But yeah, probably the filter tool would give you a better awareness of how you're doing on filtering out noise.
Wonderful. Thank you very much.
Yeah. Oh.
Yeah, it's sort of important to understand the limitations of what we're dealing with here. This tool is good for evaluating your controller performance and how to get the optimal control. That doesn't mean that by setting your these PID values at your optimal control values that you won't blow your ESCs up with the level of noise you pass through them with those filters. And there's always this trade-off between the amount of filtering you're using to keep your noise levels down. And that's why if you've heard some of my previous talk, I talk about hardware limited tunes, where if you tune it too tight, you know, ESC's blown up. Talk about noise limited tunes where, you know, your ability to tune an aircraft up to its optimal is actually hampered by the fact at that point 50% of your output's noise, and so you're actually backing off your tune to limit your noise or adding a lot more filtering than you ideally would like to bring that noise down. And so you do have to, like, you know, this is a tool that helps you work out what that optimal tune looks like, but then it would, you know, in conjunction with the filter tool, you then may be able to apply those gains to the filter tool to get a bit of an idea of how much noise is passing through and whether you are reaching unhealthy levels of noise. And the other key limitation of this tool too is it is only looking at that single state, that hover state. We then, as we're flying dynamically, we start pushing into various corners of our flight envelope, which push the system gains. We don't care too much if it pushes the system gains down a little bit, but those corners, those dynamic corners that push the system gains up and can then cause oscillation there. So your optimal tune at hover, when you start considering the entire flight envelope, may need a little more gain and phase margin than perhaps you would otherwise like to have if you're only hovering.
Yeah.
So
that's a great point, because again, it's assuming a time invariant system, right? Meaning that your gains are not changing over time. The system isn't changing over time, meaning the aircraft bare airframe. And yes, no doubt that when you go into forward flight, your bare airframe system changes. And so, you know, you're gonna have some changes there. So what Leonard's saying is definitely very accurate as to, you know, be careful. You know, if we have the ability in the future to do system ID or run the system ID, I think you can run the system ID mode in with a little bit of forward push on the stick to keep it at a speed, and then be able to then evaluate the same thing at forward flight.
yeah, and then we get our dynamic maneuvers like braking that can spike your gains, your system gains considerably. And then on top of that, you need sensible limits to ensure that while you're actually running, when you're actually hitting those saturation regions, you are coming into those saturation regions and coming out again in a controlled way. So this is really that core thing to help with that fundamental tune. And from my perspective, thank you, thank Pete, thank everybody, because this has been one of those little things that's been stepping on little change, little drops of engineering, you know, little pebbles of engineering. I'm just glad that they're pebbles and not breadcrumbs, if you know what I mean. So thank you very much.
I think the power of this tool is not only the fact that you can kind of sit down at your desk and do it, but it really, like, we have so many knobs that we can turn in this control structure. And just being able to see, like, the whole thing of like the feed forward affecting that low frequency response, like, oh wow. And I started reducing the feed forward gain. I was like, oh yeah, here it comes down. And now once I get it below a certain level, I can actually pump up the angle P gain and not affect that feed forward, you know, that low frequency. So there's, yeah, like I said, the insight it provides is just, yeah, it's really great. It just really, that's why I really like this, because it provides so much insight as to what all these knobs do and how they change your tune. And I guess one more point is, and it goes back to the question that was in the back, is I think a lot of what I'm seeing here, as far as the limits, like I don't know if this user did this out to 10 hertz. I can't remember but I think what you'd see if there was a lot more noise in the system is you'd probably see your coherence drop off earlier than what your frequency sweep went to. Like if I did my frequency sweep out to 15 hertz and I saw my analysis was only good to like 10, there's probably some noise in there that's probably causing it to not have a good coherence at those frequencies.
System ID is set up with numerous different inputs too, different input points. And so if you want to examine the high frequency response of your system, it's much more dangerous, but we do have the ability to pump those signals directly into your actuators. However, the scope for things to go bad there dramatically increases. The slowest inputs is up at the angle. So if you really want to push your upper bandwidth sections to look at ESC and frame resonances and things like that, which we haven't really played around with this tool yet, that's where the actuator inputs will potentially be very interesting. But they'll be less interesting for tuning potentially.
Any other questions? Oh.
複数 IMU があった場合、 それぞれについての IMU についてチェックすべきなのか、それとも、メインの IMU だけをチェックすればいいのか、どうでしょうか。
Right, so the question is, if you have more than one IMU, do you need to? All right, sorry. So the question from Murata-san was, in the case of flight control with multiple IMUs, do you need to perform the system ID check more than once, or is just once good enough?
So once, but I guess, how does that, it's more than one IMU, don't we use the primary IMU? I don't know that I can.
We should only be able to perform that once, unless you start getting into the realm where Andy is working, where you're pushing so fast that your IMU update rate, you're getting different IMU update rates and that sort of stuff. In our normal setup, for most aircraft that are running at a much lower update rate, all of the IMUs will behave the same. Yep.
Thanks, Leonard. All right, well, thank you.
All right, I think we're going to take a little 5-minute break. So grab a coffee, toilet, etc., and then Sanket will be up with high altitude GPS. Sanket, you want to come to the front? Funny story. The camera going. Okay. Then that's. So yeah. Okay, so you joined? Yeah. And that's you're already ready to go. Yeah. And you've muted yourself? And speakers off?
It seems like it.
Yeah, all right, great, excellent. Right. And we'll start in a minute. Sure. All right, please return to your seats. We'll start the next talk. It'll take them a couple. All right, I think we're going to start with the next talk now. So, Sanket, take it away, please.
So hi there, everyone. I'm Sankesh Sharma, and today I'll be presenting high altitude non-GPS navigation, which was the GSOC project for this year. Oh, sorry. Okay, so we'll start again. Okay, so hi, I'm Sankesh Sharma, and I'm presenting high altitude non-GPS navigation, which is a GSOC project for this year. So, there's a problem with the mic? Oh, sorry.
Quite tall. Maybe try that.
All right, maybe that will work.
Is that better?
I think that's it. Seems like.
There you go. Right?
All right.
Give it a try, a little test.
Hello. I think it's fine, right? Yeah. All right. So a bit about myself. So I'm a mechatronics graduate from India. I just graduated this year. I'm 22. And I've been GSOC contributor twice already. So in 2022, I was working for the updating ROS for ROS integration for the cartographer SLAM. And this year it is high altitude non-GPS navigation, which is a vision positioning system. So currently I'm working as a senior control system engineer at a defense startup in India. And also I'm a technical advisor for CUAV. So I think we should start. Okay. So overall, I'll be explaining what I did in this summer in the GSOC and what kind of positioning system we actually developed, plus some AI enhancements for this, so that the vision positioning system works irrespective if GPS is there or not. So let's start. Okay. So the task for this year's GSOC was to actually develop a reliable vision positioning system for UAVs to work in the GPS hidden areas, specifically at high altitude. If there's for example, loss of GPS, so at least the drone should not land. So let's assume a place the drone is far away from the home, and there's some GPS loss or some problem with the GPS. Generally, the drone will land automatically as a failsafe, but we don't know if the drone is over some water areas or something. So there should be a failsafe for that. Instead of landing at the place, it should come back to its home position, as close as to its home position, without the GPS. So it started as a RTL failsafe, but later on it actually became kind of a navigation system, as a standalone navigation system without GPS. So specifically, this thing will work specifically in case there is a loss of GPS mid-flight. Apart from that, there will be, if there's a high GPS interference during the flight, So it can take over as a main positioning system and a state estimation for that, and will obviously work for the Sentinel applications. So, but before starting out exactly how the algorithm, but why did I choose the vision positioning system? There are other positioning system irrespective of the GPS, like the Earth's magnetic field anomaly field anomalies based absolute positioning systems. But I think the vision positioning system is simple enough to start with to at least create a pipeline for the positioning system that does not rely on the GPS. Plus, it can achieve greater accuracy in case of very precise landing that depends upon some specific areas or the visuals of the areas. It can be added in as an extra help to the GPS for a very better state estimations. So over this GSOC, I implemented specifically 3 different kind of this vision positioning systems. So the first one is the SIFT feature matching. So before I start with the technology, technical of that, I should give some kind of analogy so that everyone understand it. So let's assume we are in some kind of village, unknown village. We don't know how to enter. We have a map. We know the entry we know the exact position of entry where we enter in the village, and we stroll in the village for some time, and I kind of forget where we are right now. But fortunately, we have a map of that area. We take out the map. What we generally do, look around ourselves. So, okay, I will look like there's on my right, there's a lake. On my left, there's a hill. And on front, there's a house. So generally, what I will do is take out my map and look for every kind of features on the map. Like, okay, I can see some kind of billboards over there or something like that. And I will see a specific area in the map that will match exactly the same thing. There's a lake, there's a hill, and there's a house in front. From the map, I will estimate, okay, I'm probably at this place specifically. If I just show from the image, that might give an idea. And because I know the entry point, because right now I estimate where I am, so I can easily go back outside where I started from. So that somehow I kind of localized myself based upon the features around myself. So this is localization. I'm localizing myself based on the map. So this is a similar analogy that has been used in the drones this time. So what SIFT is, so scale invariant feature transform is similar thing. It detects the features in what the drone sees and what the map it has. And similar, it look for the features, match the features from the image to the map the drone stores. And it kind of localizes itself on that map without the requirement of the GPS. Obviously, because you have a map of the area, either it could be satellite image or it could be a map you created through surveys. So it enables the UAVs to estimate its position without the GPS by comparing the 2 images. So so there are some important parameters, some technical. I won't be repeating these all parameters because so these are majorly the EKF related parameters, specifically the vision positioning system visa types and EKF EKF flow based parameters, so as to adjust the measurement noise, because obviously in case of vision positioning system, the measurement noise will be really high. So we can obviously adjust and increase all these parameters. And again, the algorithm obviously includes some basic image pre-processing like color and geometric corrections, obviously. So now let's discuss the implementation, step by implementation, how this exactly works. So if I have an area where I know the drone going to transverse or drone going to actually fly, so I will generate a map by doing a simple survey, and I get multiple images of the area. I just join them through the SIFT algorithm, because what the SIFT do actually is extract the features from each image, not map the features. It extract the features, and there's a FLAN matcher, which is nothing but some sort of differential mathematical equations that through Euler distances finds out the matching between how the 2 images match, and it joins the homograph, finds the homography and overlaps the image to create a map of the area. So once you have the map, you can put that map on the drone. And later on, when you have the map on the drone, so that will act as a reference point for the drone. So let's say the drone goes to a specific point in this flying area and it loses its GPS. So drone's gimbal, with pointing downward and stabilizing itself with downward, will start to capture the images. It will send it to the offboard computer. The offboard computer start to extract the features from the SIFT. It uses the FLAN to match those feature points from the image to the map, that has been already been given. And it starts to estimate its position, because right now I know. So as in the image you can see here, this rectangle area is what the drone is currently seeing right now. This is just a single frame. And this is the map. The whole thing you're seeing, it's the map the drone already have. So if I know where I started from, because as an example analogy, village analogy, I know where I started from. I know right now from the center of pixel of the frame that where I am currently. I will match that. I will simply get the pixel values, and there's a very simple proportionality between the camera's intrinsic parameters and the real world coordinates is that they are proportional to each other. The offset in the XY axis in the real world upon the height of the drone is proportional to the XY pixels distance in XY axis upon the focal length. We know the focal length. We know the pixel distance from this algorithm. We know the altitude through barometer. We can just plug in all those values and we can get the offset in the x-axis and y-axis in the meters or in centimeters. And that will help us to get the precise position of the drone. And we can send it through vision position estimation MAVLink messages to the drone so that it can start to localize based upon the local parameter, local coordinate system. So overall, a lot of optimization is required in this thing because SIFT inherently is very much, it takes a lot of processing. It takes a lot of compressing actually, because you need to compress the image so much so that at least I get the 4 Hertz. That is the requirement for the EKF at least to stably estimate the state. So that's one of the major drawback for the SIFT part. But overall, if the compression and all these things went well, so I can get the 4 Hertz minimum rate from the EKF and send the data over the vision position estimation, and I can localize the drone without the requirement of GPS. So a very basic example how I create the map. So this is the data set of images that has been taken from a survey, and I will just send that to SIFT, find the homography, overlap the image, and I can get a bigger map of the area that will act as a reference point for the drone. And here's a video that will show the working of this algorithm. Sorry. Okay. I think it's visible. Drone in GPS when it has the access to the GPS, and after it takes off, I have already set the EKF source, second EKF source to not using the GPS and already relying on the external position estimations. So when I turn off the GPS and change the EKF source to the secondary EKF source where it do not have access to GPS, the drone will start to take the camera frames, match it to the already existing map it has, and it starts to localize itself without the GPS. So I will just, okay. I turned off the GPS. I started the secondary EKF source, and you can see the drone starts to move a little bit because there's a little bit of drift, but it keeps on correcting itself. And right now I can even use the loiter mode to actually control the drone. That I will do right now, just a second. Yeah, so in the loiter mode, even I can control the drone without the requirement of the GPS. So that kind of acts as a positioning system for the drone, this SIFT. But the only major problem that I discussed earlier is the rate we need to get, the minimum of 4 Hertz. That's really difficult to get with SIFT. So why not use it with some other approach that why not use it with some other approach that can give us a rate, the position rates at a higher position rate. We can get the position at a high rate, and the feature matching will work alongside it so that it corrects the drift from that thing. So best approach would be using the optical flow. So if we use the optical flow, we can get higher rate position estimates, just directing it's getting the flow rates. And alongside, we can run the SIFT feature matching. So whenever it gets a good match, that's pretty much like it knows that it precisely is here, we can correct the drift over time. So in the optical flow approach, generally a very famous algorithm is Lucas-Kennedy method, which is generally used in most of the optical flow sensors already. So I modified it a little because the drone will be moving at very high altitudes. At low altitude, the optical flow work very well because there's a constraint in that at every consecutive frame, it estimates that the brightness of the pixel remains the same. And that's not the case, obviously, at high altitude. Sometimes drones will move fast, sometimes drone will be slow. So what I applied was a multi-scale pyramid representation. What it does is just when it takes the camera image, it scales it it scales it for multiple levels, smaller, greater, and greater, and it estimates the optical flow vectors for all these frames. So optical flow is nothing but just solving a linear equation after Taylor series linearization. So just solving the flow vectors equation for flow vectors variables from the equation. and getting the flow vector. So I get the flow vectors from all of these different scales, and I get a good estimation of the flow rate, and I can simply just dead reckon with those flow rates and use the onboard IMU to dead reckon that. Alongside that, what I can do is I can, on a secondary thread, I can continuously run the shift feature matching and run it until I get a very good match, so that I know that the drone precisely is at the specific place. So what I do is, as soon as the drone takes off, I start the optical flow. The drone obviously work as an optical flow because of the multi-scale pyramid scaling. The drone can go at a very high altitudes already. So after high altitudes, it starts to drift a little bit. But because the drone already has the map and it finds out a match, there's a Loess ratio Loess ratio test, which estimates if we have a good position system. If I get shift features for, let's assume, greater than 30 points, so I know that it's a good match. So as an example, this image at bottom, not so good image, but yeah, let's assume the drone needs to go at the straight path that has written the actual path. But because the optical flow is turning, there's obviously a drift. It starts to drift a little bit to the bottom side here. And at the middle, let's assume the feature matching find out the absolute position. Okay, so I'm drifting a little bit. It starts to averaging out the values that it needs to be plus where it is. It starts to correct slowly to where it needs to actually go. So kind of just merging this to the high rate estimation of the position plus the low rate feature matching for an absolute positioning system, I can get a reliable system for the optical flow implementation, for this implementation specifically. And there's a small video for that too, this implementation also. Okay, so as the optical flow drone starts to move, these optical flows, these are calculating the flow rates. And alongside on the secondary thread, a shift feature matching is also working. So as soon as the drone starts to drift, currently it's in the non-GPS, it do not have an access to GPS. So SIM GPS disable is turned on. So it's not having the GPS right now. So as soon as it's moving, I am commanding it in loiter mode. As soon as it starts to drift and it's find a good match on the map, it starts to correct itself over time. So as it does not drift a lot from its actual path. So the result from the optical flow and the feature matching seems pretty reliable. And obviously these things work very well, but the thing that we have not considered are the clouds, are the water or the area that do not have very much specific feature points. So specifically the main challenges in the vision positioning system, the traditional algorithms of the VPS positioning systems is that, first of all, resolution, angle, and lighting will not be same in every case. You made a map today. Tomorrow there will be less light. There will be different perspective of the camera. There will be different lighting. And obviously this thing won't be working with the satellite images because it works generally on the intensity of the pixels, just the change in the intensity of the pixels. So these things won't be reliable in the case when we have a satellite image or there's a lot of changing in the resolution, angle, or lightings. Second, again, as I mentioned, clouds and water reflections can cause inconsistencies in visual data. If there's a cloud cover and the drone is flying really high, it won't be able to see every part of the terrain. So it won't be working that way also. Plus maintaining a consistent high rate, as I mentioned with the shift, the 4 Hertz. It's really difficult with the shift because it takes a lot of memory. So what can we do in this situation? So the best friend, the AI, the transformer model, the recent release, the chat GPT and all, the transformer model that they're using, that they have changed everything regarding the AI space. So what the neural networks can do is, instead of matching all the specific pixels on the very basic mathematical equations like Laplacian of Gaussian and to find the edges and to find the estimations, it can just get a smaller part of the image from the cloud cover. It can, using the neural network, it is trained on the transformers. It can find out exactly where it is without having to rely on to get a very specific, good, clear image for that. So how does that work actually? So let's see for the transformer. So I won't be giving too much, won't be discussing too much about the vision transformer. But as a basic thing to understand how it works is, for example, we have an input image of satellite image, not the map. Right now we can use Google Maps or anything that can give us a satellite image, or we can just download a satellite image from Google Maps or anything. We can get the satellite image, store it on the companion computer. So what does the vision transformers actually do? It converts the image into small patches. And it takes each of the patch, it converts them to a mathematical number, which we call the embedding. So just for the computer to understand, it creates a multidimensional array or the multidimensional embedding the mathematics in the numbering thing. So let's assume it gives each patch a 2-dimensional embedding. a value, it's just a mathematical number. And the main thing about the vision transformers, this specific model, is the self-attention mechanism. So what it does is, if, for example, I have a satellite image and I have a drone image, it tries to find out the cross correlation between each patches. So for each patch in the first image, patch is just small part. And for each patch in the second image, that's what I'm getting from the drone. I found the cross correlation between each of them. I get a number. So the closer the two numbers are, the two patches are more similar. If I explain in a very simple manner. So if I have a specific place over, for example, a building, I get that patch from the building on the image, the vision transformer will get. It will get that specific patch from the map. It will try to find the cross correlation. And the best thing about this, we have a relative numbering in that. In case of SIFT, we do not have any relative system for that, because the SIFT is just some mathematical equation giving us if it's a good match or not. But here because every patch is cross correlating with each other patch, we have a specific number for each a specific number, which defines the relativity with the other patches also. So when the two patches have the very close number, like for example 33 and other patch has the 32, obviously it will be an n-dimensional array, just to simplify the things. One has a number 33 and the other patch is 34. So I know this patch is correlating with the patch on the satellite, a satellite image. So I know the drone, precisely where the drone is right now, because the numbers matches a lot. And if I am able to do that, obviously I can localize the position. And because the vision transformers right now getting so fast, I can easily get the rate of up to 5 to 6 hertz. And if I can just optimize it a little bit for a specific use case, I can easily get up to the 10 hertz. So as I mentioned, the global view and all these focusing on important features, because it's cross correlating between multiple patches already. So I think the implementing the vision transformers seems a pretty good call for this thing. So there are actually two very popular already available transformer models, vision transformer models. So the first one is DITA. So this is a detection transformer. So what it does is, so the first approach, what we can do is, if we have a satellite image, we can run the data. So just think about it, some object detection, the data. But at the back end, using transformer models. So it can detect, okay, there's a building over here. There's a static like road over here. There's this other kind of building over here. And it can look in the map also. The satellite image, it can find out, okay, I have this pattern. The building is here, the house is here, the car is here, something specific is here. And I can match that to the satellite image, where that exactly is. The first analogy that I mentioned, the village analogy, and it's literally working like a human eye would work. It will find the same pattern of the buildings where each being placed. It finds out on the secondary image, and it can easily localize itself, because it knows I can find this pattern in this specific area. So the data works that way. The only problem with the data is that because it's the object detection only. So it can only classify the buildings at all. So two buildings can be same. If we are in we have the multiple buildings over there, this won't work, because it cannot classify how the one building differs from other. So we might have something much better than data, and that is Lofter. That is local feature transformer that worked pretty well to match the satellite images. So instead of detecting the objects like buildings or just car or a pond or anything, what it do is it stops at the part where I just mentioned, like the cross correlation and the number. The moment it gets the cross correlation between the two patches of the image, it finds out, okay, these two numbers are pretty close. The two n-dimensional tensors are very close to each other. It stops there. It tells, okay, these two patches meet. And again, what the SIFT does, it do with the data that it is trained on. So instead of, because SIFT can only SIFT and other like orb and all other these mathematical feature estimations can only do when there's can only work when there's no significant change in the scale does not change a lot, and all these things. But here, because I can do the course level feature extraction as well as the finer details also. Plus, as we have the positional encodings also in the vision transformers, we can easily find out where exactly the drone is, because we know the position on the image. We can easily localize itself there. And we have a relative confidence-based matching refinement, which is not available in the other cases like SIFT and all, this basic algorithm. We have a specific relativity. We can find out how much this patch relates to the other. The only problem with this thing is the data. The data to train these transform models requires a lot of data actually. So to actually get that much data and to train it on is really a challenging task. So I and Rice are already trying to get the data for this to train it on. But let's see how it goes. But overall, the lofter works the similar way. It finds the unique features, it correlates each other, and it matches the key features and find out the location. So this is just an image. I have not tried it very much with the videos. So one is the satellite image, and other one is the actual image from the drone. It pretty much is able, and very low data. It's just trained on few thousand images. It is able to find out, match the positions on the satellite image where the drone currently is. And we can again just use the same analogy, like we can find through the pixel values where the drone is in the local coordinate frame. Overall results, SIFT proved to be highly reliable. The only problem with the SIFT was it cannot provide the data at very high rates until it is compressed a lot. And after it is compressed a lot, the problem with that is it does not find all the features precisely. The optical flow is good, but the drift it adds, plus these cannot work in the cloudy environment or in the environment that do not have too much features. So these can be enhanced using Lofter or these transformer models. We can even construct our own transformer model architecture, and we can easily map the complex environments. So what could be the next would be just making an architecture for the vision transformer specifically for the use case, because there's a lot of research is already going on this part. So there are some companies already which are working, which are just using the SIFT or some other algorithm. But the only thing they are not yet able to find out, again, the cloud cover, they cannot fly over the cloud cover, and they generally it works very well. The SIFT works very well in in planes, because planes can dead reckon for a lot longer as compared to the copter. So they can easily use the optical flow. They can easily dead reckon and use the SIFT feature matching to actually localize them itself. And we can implement this EKF resets over a long time. So there's an EKF reset command, which can be used to reset the EKF when it's drifted a lot. So Lofter and all this can use this. So that was all from my end. And thanks a lot. So if there's any questions.
Have you given any thought to being able to search features if you need to find your position again after a long period of cover, or if you don't know an initial guess?
Yes, we can. Yes, if we do not consider the time in that case, in case of SIFT, which I tried a lot. So if we do not have the initial guess, but the overall perspective, the light change, as I mentioned, are not change a lot. The very first guess will take at least a second or 1 second, a second or two to at least get the initial guess. Then we can use approximately a nearest neighbor algorithm, so it do not searches the whole image continuously. It keeps on searching the local area as the drone moves. So the initial case, if it do not know where it is at the beginning, it can take a second or two, but later on it can start to produce the data at 4 hertz or 5 hertz.
Thank you for an interesting talk. I wanted to get more of it for which altitudes this can be, or like what will be the lower threshold.
Okay. So this optical flow, because it's optical, it can start from a few meters also, because the optical flow works at that distance only. But on the simulation part, I tested it up to 150 meters already. Above 150 meters, it starts to actually misbehave because of the features and the cloudy thing. I have added the cloud in the simulation. But the Lofter part, which I tried with the cloud cover, a little bit, I don't have photos, I guess, but yeah, I tried it with cloud cover, which has a very minimalistic view of the actual terrain. And it was able to precisely find the location within a meter or two where the drone is. So yeah, I think it will obviously, the Lofter and this transformer model, I think, will work up over 150 meters also.
So if I understand you correctly, the lower altitudes are less of a problem, or more, are the lower altitudes less of a problem?
Yeah, lower altitudes are less of a problem, right?
Okay, thank you.
Yeah, so thanks. First of all, thanks very much, Sanket, for your work. I think it's really great, and it's a feature that we hear a lot of people want. And I think you've done a great job at sort of setting the roadmap, at least, and more, I think. One question is it when you're using the visual transformers, is it important to make it easy for those transformers by, say, for example, rotating the drone's, live, picture or video so that it probably matches, say, for example, like Google Earth's maps? Or, another idea would be, I guess, is it important to, zoom in or out, I don't know, the pictures from the map to match, what the drone is seeing. Is that kind of, simple transformation helpful before you pass them into the visual transformer?
That can actually help. But the thing with the visual transformer is they find the gradient for each of the patch that they get. So they know what the orientation is, and it automatically, using that self-attention mechanism, it find out where it actually is. So the transformation, which obviously just might help us with the making it a little bit faster. But I think the vision transformer can work pretty well with the different kind of transformations already.
Cool, thanks.
Hi, Sanket, great talk. We heard some benchmarks as to, SIFT was giving you trouble running at higher rates. What sort of architecture were you running this on? What are those benchmarks based on?
All right. So for the simulation part, I tried it on, I used a GPU-based SIFT also and a CPU-based. For the CPU-based, it was i7 12th generation kind of CPU, and for the GPU, it was RTX 4060. So on the CPU one, I was getting barely around 4 to 5 hertz. And with the GPU one, though GPU one does not work really well, but yeah, I was able to get up to 6 to 7 hertz. Sometimes when it's transversing, but sometimes if you do not find the match pretty well, so it just decreases up to 1 hertz or 2 hertz in that case. But on the, if we test, I have tested on a video on NVIDIA Orin NX. So I got up to 4 to 5 hertz on the NVIDIA Orin NX with the GPU based SIFT. But that also depends upon if the clear view of it, the drone is getting a clearer view of the terrain or not. So it can range anywhere between 1 to 5 hertz. So yeah.
And this is a standard OpenCV implementation.
For the SIFT based, the CPU based SIFT, it is a standard based. But for the GPU based, I have made it modifications because the existing GPU based SIFT does not really work with the Python, or even in the C++, does not really work well. So I made some minor changes to SIFT so at least it can scale the pyramid, as I mentioned, the multi-scale pyramid. I implemented that on this GPU based SIFT. So at least I can get a much reliable position because the GPU can work on a much higher rate. Yeah.
Thanks.
「日本では結構山とか田んぼとかってあるんですけども、私の方では産業用と、農業用の、ドローンを作ってるんですけども、その中で、田んぼだと同じフィールド、同じ模様なんですが、そういったものの中で GPS がロストした場合、あと山間部の、山マウントとか、そういったあまり変化がないようなところでの、位置の精度とか、それが知りたいなと思いました。ぜひ、すごくいいアイデアなので、検証してみたい。
Yeah, so the question from Murata-san is, here in Japan, we have a lot of mountainous terrain. And also, I believe his company works on agricultural drones, and they're often flying over rice paddies, which are very similar. And so he wonders about, how good the quality is in those situations.
So specifically mountainous areas, specifically in mountainous areas.
Mountainous areas, and also areas where, could be rice paddies that all look very similar. And how does the algorithm work in those situations?
Okay, so if the features are, yeah, so in that case, if the features are already very same, like the paddy field, so it won't be working really well in the paddy field because obviously it cannot distinguish between if the specific patch differs from other patch. But in case of the mountainous areas, if it's flying really high, that probably might not be your question, but yeah, if really flying really at high altitudes of the mountains, that can really work well because we have the terrain SRTM terrain data set also available. So we can actually map the positions from that, and we can actually localize our mountainous areas also at high altitudes.
Thank you. ありがとうございます。
All right. Thanks a lot, everyone.
All right, our next speaker is Patrick. isn't it? Yes. Yep, Patrick, please come to the front. Oh, cool.
Hello, my name is Patrick. I work for Blue Robotics, a company that develops ROVs, remotely operated vehicles, as the Blue Boat, unmanned surface vehicle. The company also provides the building, or like the basic foundation for developing other vehicles, and it's pretty popular. My idea here to talk about MAVLink tools, so some of the tools that we use, there are the base for mostly for software development. And the subtitle is Tomorrow's Solutions for Today's Problems, because I see that some people are using, but I believe that some use case, the use case that we're seeing here, could leverage the tools that we use and can collaborate with us for further development. So one of the phrases that fits really well here is that the people who have the greatest impact in the world are annoyed when they get stuck doing boring chores that could be handled more efficiently. And that resumes pretty well most of the tools that I'm going to talk about. In the past, we were using Companion. It was a fork of the ArduPilot old Companion software. It was a monolithic node-based software. It provides a really basic abstraction for the user to command line interfaces. At the time, it was Mavi proxy and the JStreamer command line too. And for a user experience, we had a lot of problems. First is that a user needs to have technical background to configure MAVLink endpoints, and also technical background to deal with camera pipelines. And this is pretty complex. If someone deals with the JStreamer pipelines, no, that's not an easy task. You need to know somehow what you're doing, and there are some magic things that you need to know and be aware about when creating pipeline. Otherwise, the user can have a really poor glass-to-glass latency between the camera feed and his computer or ground control station. In the case of IHV, a remotely operated vehicle, you have a tether that connects your surface computer with the vehicle, and you have directly internet link. So we have this directly internet link that provides the MAVLink data as well the camera feedback. And as you can see here, we have the Mavi proxy configuration and also the camera setup, where the user can change the JStreamer pipeline, and also the video for Linux controls that are available via the video for Linux interface. And at the time when doing development, we thought that it was kind of hard doing development based on these and using these tools. So we tried to create something new. And that's what I'm going to talk about. One of the first tools that I'm going to talk is MAVLink Camera Manager. It's already 4 years old, a really small child. It replaced hard-coded JStreamer and FFmpeg pipelines with friendly interfaces. It was in the final era of our old Companion software. We are already starting to use it, and we started to adopt. So it provides a REST API with stream management, thumbnail generation, and also camera control. Camera control, at the moment, it just supports video for Linux, but our target is to support also on-Viv controls for IP camera-based assistance. In the case of ROV, usually have like more than one camera. So supporting IP cameras, multiple IP cameras on the same network is kind of a requirement and really good thing to have. Something really cool that also provides is WebRTC support. And this allows you to have a really small glass-to-glass latency to web technologies. And as an example, you can create a web-based ground control station if you wish to, because you can have this video feed quite easily. As I said, IP camera support multiple and different streams. I'm going to talk about that further. And also automatic vehicle setup. This is really cool because if a user or someone that is dealing with the command line interface of the camera manager wants to support a specific vehicle, not necessarily the Blue Bolt or the Blue AOV, you can configure the system to automatically generate the necessary video streams for this specific vehicle. And for companies or people that just have their own vehicles, they can easily add this really small flag that specifies the vehicle name, and the camera manager automatically deals everything with the camera stream pipelines for you. This is the GitHub page. As you can see, we have plus 90 stars. This explains a bit more with what the project does. As I said, full REST API. As showed yesterday, we also have a full Swagger documentation of our entire API as well. For developers and users that want to take a look on all possible functionalities, they can go there and take a look. Also, there is SDP files for people that just want to use third-party video software like VLC. They can just have as argument the SDP file or SDP source. And with that, you can have the video stream play in your ground control station, your VLC, or any software that you wish to. We also have support to the MAVLink camera standard, where you can easily connect with key ground control or other ground control stations that support the MAVLink camera standard. Here is a really simple example of the interface. The development interface is not the final user interface. But the really cool thing here is that you can just run it right now in your Linux computer. If you have JStreamer installed, it should be ready to fly. As I forgot to say, we also provide binaries for our architectures, ARM 32 bits, ARM 64 bits, Windows, Linux, and Mac, x86, and ARM. Windows and Mac doesn't have support to JStreamer pipelines, but can work with redirect video streams. So you have IP camera, you can redirect your video stream through the camera manager and make it able to work with ground control station. And I was saying, the development interface is quite simple. You have all this data that you can configure your video streams and also watch your video stream directly there via the WebRTC source. But this is just a development interface. It's ready to use, go, and that, no problem. But nothing is holding you to develop a really nice interface where users can interact with it quite easily, like having checkbox to enable thermal and disable, like enable and disable thermal cameras, configuring UDP or different types of RTSP streams. One of the clients that we had, he had problems having RTSP, and we added support to multiple different RTSP types, in the case that UDP, TCP may not be working quite well on the network environment. And of course, it's a really nicer way to configure and deal with your camera stream. And the camera manager is quite complex. This diagram explains a little bit what it does. Well, it's JStreamer based, it's ready to use binary, except you need JStreamer DLLs. We're not providing it. You can install via your operating system manager. Is integrated with control stations, which follows MAVLink camera protocol specification. One thing that we try to do as much as possible is to avoid transcoding. We put a lot of time on the JStreamer pipelines that we use, because if you try to do video transcoding in the media, you increase this glass-to-glass latency. And we try to decrease it as much as possible for user feedback and control on the vehicle. We try to target around 125, 150 milliseconds between the camera and the surface computer. And we also get really good times through WebRTC as well. The latency that we add through the camera manager is really small. The software is good, and to me personally, is the best video stream software for like if you have a Linux computer. If you're not using MAVLink, it's still great. But we also like it was done to firstly to support MAVLink and deal with the key ground control at the time. And things that we're working on is video recording on the vehicle side. This is important because sometimes you are flying a vehicle or you're piloting an ROV and the connection may break in the middle. So for that, we are trying to record the video locally or recording chunks. So if you are also recording the video in your surface computer or your ground control station, you can also recover chunks that you are losing and recover the entire video stream on both ways. You can have the video stream saved on the vehicle side, or also recover specific frames on the on the surface computer. Audio transmission is something that we are working on as well. We think about subtitle generation for on-screen display and integration with a pub/sub architecture for people that are using RAWs or something else to just easily take average of it and have the video feed directly from like a RAWs node over integrating with a UDP source if you wish to. And well, multiple APIs, command line interface, REST, MAVLink, SDP. We have inputs via USB cameras, CSI cameras, RTSP, all with. We are working heavily on H265 because of the bandwidth issues that people may have. And of course, for outputs, we have UDP, RTSP, WebRTC, and also thumbnail generation if someone wants to take snapshots. The other project that I want to talk, before, let's just showing up really quick. So here I have camera manager working through BlueOS. As you can see, I have snapshots here on the little camera, and you can just go here and configure the video stream and change the brightness or change the contrast of the video stars, like quite easily for controls configuration. And of course, I can come here, modify or create and add, like change the size, frame rate, UDP, ATSP types, we put different endpoint formats. And this is a really simple interface that you create for the user. And of course, if we enable part mode, something really cool that we have in BlueOS that you can just enable full power of it, you of course can configure different PSM 2535, 2035 here on the Raspberry Pi 5 that I'm running locally here. And of course, creating fake video source for raw video development and much more. It's quite complete. Moving on. The other project that I want to talk about is MAVLink to Rest. It's a project that I started 5 years ago with the idea to empower web technologies on the ground control, like for drone in the drone industry. I was really happy 4 years ago because I got it working, like the REST API was working. At the time, I have not completed the WebSocket functionality. But I remember that posting that really happy on the ArduPilot forum, talking, hey, I have this really nice tool that can use for people to just integrate web technologies with drones directly. And it was really exciting at the time. It was the basic foundation for BlueOS and our development on web technologies that integrate with the vehicle side. It has almost the same number of stars. It supports all operating systems. And it provides multiple functionalities as complete REST API for every single message that you can see there from the MAVLink standard, and also WebRTC where you can see in real time the MAVLink message. It's not raw MAVLink message, but JSON-based MAVLink message, where you can easily integrate with JavaScript or any language as Python. So sometimes I'm doing development, I'm just open Python, and connecting the WebSocket, if featuring the messages, I like maps. Or much nicer, you can also use WebSocket and JKey to filter the message directly on a terminal. So if you want to investigate and debug MAVLink message, you can do directly on the terminal without writing a single line of program. To a small demonstration layer. It's a critical service. It's a service that is like it's the basic foundation for everything that we do. Starting in the mid-2019, is a MAVLink, as I said, MAVLink serializer, deserializer for JSON 5. It's not JSON, it's JSON 5 The difference is that JSON5 is a overset of JSON where it supports comments, it supports undefined values and other cool things. It's really interesting because you can just have extra functionality over JSON. The idea is to empower web technologies to interface easily with vehicles, provides RESTful API and WebSockets interfaces. You can friendly access message values and fields. As I said, you can have every single message, MAVLink message as a REST API. So you can do like -MAVLink, -heartbeat, like system ID, and you can have the value there ready for you without dealing with MAVLink at all. So everything available via REST API. And of course, you can have WebSockets filtering by message names. So if you create a WebSocket, but you just care about the heartbeat message or just care about the attitude message, you can pass it as a query parameters. And it's a reject. So you can also do some fancy things with it if you wish. It provides a basic front end with status visualization of the message, the frequency, the last message time, and of course, to visualize the message, and delivers a TypeScript definition of MAVLink message. So besides MAVLink to REST to exist, it also provides a TypeScript library where people can average MAVLink to REST in a safe way, where all types in all MAVLink messages are defined in TypeScript. And this ensures that every single access to the MAVLink message are defined through the TypeScript definitions, making the code development safe. So if we're trying to access a field that doesn't exist on a specific MAVLink message, the software will say, oh, there's something wrong here because this parameter, or this property doesn't exist in this message. And this makes the development really secure. And in the diagram, you have direct connection with the vehicle. You have also the history of every single message received, the last message. And with that, you connect directly with the REST API. So every single message received have a history, and you can take a look on it and see the message that received. And with that, you have the web server that creates a WebSocket connection directly to the vehicle. So when you have the WebSocket, is WebSocket vehicle, and you can communicate directly with it. The message that you're receiving or sending are just abstraction over JSON. So if you want to send a heartbeat, if you want to receive a specific message, you are directly talking with the vehicle with MAVLink to REST to be the man in the middle that translates JSON to MAVLink, MAVLink to JSON. And this is really cool because it empowers web technologies in a really fancy way. In this case, you have Node-RED. Node-RED is a block-based programming language that people can just drag and drop blocks and program really small JavaScript. And in this specific case, they are using MAVLink to REST to receive MAVLink data. And also it's connecting through serial port to a solar panel. And it's getting data from MAVLink to REST. It's getting data from the solar panel. They are saving both together a CSV file, also getting the data from the solar panel and injecting it to the MAVLink feed through Node-RED and MAVLink to REST, and simultaneously is also creating a dashboard for data visualization. Since the solar panel data is also being put on MAVLink to REST through the MAVLink message, you can easily see that in the UAV log viewer, where you can see everything integrated. So this user, he didn't need to to program something really fancy. He just dropped some blocks, connected it, take a look on the API, and was able to accomplish this really interesting tool where they can investigate and see what's going on with their boat. It's a really cool example of the power of MAVLink to REST. Another one is BlueOS itself. We have the heartbeat icon to be sure that the connection is available. You can access parameters quite easily through the parameter protocol. You can fetch information from the flight controller. And well, everything that can be done through MAVLink can be done via web technologies as well with MAVLink to REST. The difference here is how you're going to do it and how much time you're going to put on it to make it pretty. And that's really interesting. And of course, it's also possible to do web-based ground control stations. So in this example here in Cockpit, we're going to have a talk tomorrow about that. It was entirely based on MAVLink TRS to provide, to get and publish data via web technologies. And of course, getting data there from the video using the camera manager with WebRTC. And as stalking, it's quite easy to arm and disarm a vehicle through MAVLink TRS. In this case, you have curl with a request to post. And okay, my system ID is 255, my component ID is 240. And I'm just want to send a command long that type mav command component arm disarm. And I can just change it to 1 to 0 to arm and disarm the vehicle. And yes, it supports comments because it's JSON 5. So for a user, this is really cool because you can see the comment, you can copy and paste it. And the comment there is easier because the user knows what this parameter does because there is a comment there. And since he's going to paste this command on the terminal, he will be able to see the vehicle arming, disarming. And of course, this consequence of it is the base mode bits changing from one to other. And to visualize it, you can use WebSocket and JKey. WebSocket just connects a socket and makes it available through the terminal. And JKey is a command that helps you to deal with the JSON. In this case, I'm selecting message type heartbeat with component ID and system ID of 1, and I'm printing the message. So just to show here example really quick. In this case, I can have WebSocket working here, and I'm printing, well, it's not showing very well, but trust me, it's printing the heartbeat. So it's printing the heartbeat. You can see the bits as 81. So if I try to do a curl post as arming the vehicle, you can see that the bits mode changed to 209. And of course, I can disarm again the vehicle. Oops. Changing the parameter type to, oh my God, change the parameter type to 0. And the vehicle is disarmed. Really quickly, really easy, JSON, friendly, nothing to worry about. And of course, there is also the comment there. I'm posting the request with the comment. So like, I know what this parameter does because there is the description there. Okay. Saying that, 2 point, MAVLink TRS and camera manager, they are not just development. Well, more than 4 years there. We have over 3,000 vehicles running BlueOS. Yep. And these vehicles are running the camera manager and MAVLink TRS as the basic blocks for everything that we are doing. And we have over 170 daily users. So everything is quite fine. And based on our experience in development BlueOS and these tools, we also have another tool that we are creating based on everything that we learned. And this tool is the MAVLink Sava. We started this year during the company meetup. Is one broker to roll them all, and that's the description of it. Replaces MAVLink routers, MAV P2P, MAV proxy, and MAVLink router. But not only that. Is multi-thread friendly. It provides an interface based in WebAssembly. It helps you with data visualization. It helps you with like easy integration with other drivers. It has a ready-to-use binary as all other softwares. So you can just download it now, run, connect through serial, UDP, TCP. You know, it's your choice. It is going to work. It supports the old connection like UDP source, UDP in, etc. as UDP out. The same command line to MAVLink router should work in place with MAVLink Sava. And of course, we also have a new way of doing it where you can just use specific parameters where you can filter specific system IDs, component IDs per connection link because of performance issues and other things that people can average and just do the best that they can do with the MAVLink Sava. It's based on the async Tokyo framework in Rust. It has statistics per message, per drive, bytes per second, how many, like everything that you wish to have the statistics It's quite good because sometimes you need to debug MAVLink message and debug the MAVLink communication between the vehicle and the ground control station, and have this data is really interesting. And also allows you to add and remove drivers on the fly, different from MAVP2P, MAVLink router, if not mistaken, MAVProxy. Not sure 100% about MAVProxy, but it provides a REST API where you can easily create and remove endpoints, MAVLink endpoints, without restarting the tool as a normal service or web service. And the idea is to have more things as rerun integration for MAVLink data visualization, and also like Lua integration, and everything is possible because of the software architecture. The software architecture is quite simple. This was work of João Antonio. He put a lot of time on this tool. João Antonio is maintaining most of these tools nowadays. And we are moving MAVLink to REST to MAVLink server because it's just another driver for MAVLink server. So at this point, we are working still on REST API and web frontend. Like we are working also on Tom for like custom description files of MAVLink endpoints, and also ARPL. We support UDP, TCP, file to log for read and write, serial, REST, WebSocket, and soon we are working to Zeno, Lua, and other drivers as well. Another interesting thing, we also have fake source. Fake source is like a MAVLink fake data source, so you don't need to have a vehicle to test a ground control station. You can just use a fake source to test your entire MAVLink pipeline and see how things are working, and see if you are losing message from one point to the other in the network when you have multiple MAVLink servers connected. And just to show here really quick, we can go on available services on BlueOS and take a look on the MAVLink server here. And let me see if I can make it better. Better. So as you can see here, you can have all the messages being received, all the statistics per message, number of bytes, delay, timestamps. And of course, if I want to take a look on the attitude of the vehicle, I can just take a look on the attitude message, right? And if I want to see the pitch or roll of the vehicle, I can just put the mouse over and I have the pitch there quite easily, right? And not only that, it's real time, so I can move here my Raspberry and whew, it works. Of course, every single message, every single value here that we are seeing is being plotted in real time, thanks to WebAssembly. Works really well. And the statistics here are per message. Of course, they are not connected because we have our own MAVLink parser that João Antonio put a lot of time on that to make it the fast and the best that we can. So we have the non-MAVLink message that you can see here based on the fields that we are plotting. But at the same time, we are aware that people can receive MAVLink messages that we may not support, or they are not documented, or they're in development. And with that, we can have also the statistics information on every single one of them here. And well, as you can see, it works. And that's all. I would like to do special thanks to Blue Robotics for being here, also ArduPilot to creating this really awesome event. The MAVLink, João Antonio for helping me with these tools and now being the maintainer of them, and also all the collaborators and contributors. And that's it. Questions?
Hi, thank you for the talk. It was really good. I'm going back to the camera manager. Apologies if you addressed this back then, but there are some cameras coming out like the Sony ILX, for example, that have their own SDK hooks. Is there a way to work with that using this camera manager at the moment?
Well, if it supports Linux, it should work out of the box. If you have a GeoStreamer like element, it should work. There is also the advantage of it's something that Camera Manager supports, to create our own custom GeoStreamer element that use the SDK. and just take advantage of this element and have it working. But if it works out of the box on Linux, it should work out of the box on the Camera Manager as well.
Perfect. Yeah, that sounds great. Thank you.
Hi, thank you for a great talk. Great to see all the features that you have developed. I was curious about many things, but one thing I wanted to ask about was the MAVLink server. So that runs on the companion computer, but then it also connects up to your cloud, or?
So the MAVLink server is just a MAVLink broker or MAVLink router. So you can have it connecting like one MAVLink server to multiple other MAVLink servers in a network if you want to crash, or just do a direct connection. For cloud integration, you can just have a single MAVLink server that sends the data there. Or if you want to broker on the cloud, you can just have another MAVLink server. It's just a bridge. It's your choice to use it when you as you wish.
Okay. Yeah. Thank you.
I really love that MAVLink server. It's very interesting. The fake source, I mean, I'm assuming, but can it be just a standard bin log?
Yes, it can. So at the moment we have T-log support. We don't have binlog, but this is just a matter of time. So what happens at the moment, at exactly this moment, when you have a T-log, it's just parser as fast as it can. So, but the idea for us in the coming weeks is just fix that and having it playing in real time. I think it may already do it. It just be like a parameter when created the T-log endpoint as source. But for binlogs, yes, it's totally doable. We use a fake source because sometimes we're doing development and we want to test creating MAVLink message as fast as we can, just to test the entire bandwidth or doing the connection between my computer and the IOV and seeing if the connection is good enough or if you're losing packages or something is happening. So it's just a way for testing MAVLink connections between network environments. It was based on the fake source of the JStreamer pipeline, and you can create like this ball moving, and you can just test your JStreamer pipeline. We did the same thing with MAVLink. We could just generate random MAVLink messages for you to test your MAVLink connection on the network environment and see if everything is working. And of course, with the data from every single message and endpoint, you can also visualize if something is going wrong.
Thank you for interesting presentation. And I have a question about the camera manager part. And we also do streaming through the mobile network. And almost every time we faced the bandwidth issue. And my question is there a feature to change the resolution or frame rate before the bandwidth getting worse?
Yes.
Or a issue to shut down the streaming also.
So at the moment, you can change the video size, the resolution, and also the frame rate. Yeah. You can also do it, how can I say, you can also use different output types. As I said, your network may be having problems with like UDP, but TCP may be working better because of your network provider in mobile. We saw this happening. So depending on how you connect your video stream, you may fix these issues through like just tuning the RTSP connection.
Is this automatically changed?
No, not automatically changed. Oh. Because some things, it can be done. Like if people want to collaborate and help with that, can be totally done. We don't do it at the moment because of time. We are working on other stuff. And the possibility in the future is also to allow transcoding if the hardware has the possibility. So if you have an NVIDIA board and you can do transcoding in real time, the WebRTC stream can dynamically change the resolution. We are avoiding that because of the latency issues, and we are running a Raspberry Pi 3. Some products like we're still running Raspberry Pi 3. So the camera manager and MAVLink Rest, they need to be to have the best performance that they can to deal with this hardware that we're using.
Okay, thank you.
So one more question more about the camera manager. So what if you have, if we want to have our own signaling server, for example, if we don't want to display it through a web browser running on the companion sorry, a web server running on the companion computer, if I understand correctly.
So we have our own signaling implementation. The signaling also was developed from us. It's not like the problem with signaling in WebRTC is that every single person has their own signaling implementation. But we have the signaling client and server done. And if you want to develop your own video visualization, WebRTC visualization, you can take a look on the camera manager because it's there. So if I come here and go directly on the camera manager and take a look on the new WebRTC site, add consumer, and also add a WebRTC session. Yeah, here the video is working. Hey, so you can just use this WebRTC signaling client that we have here. The implementation is there, is open source. You can just copy it and have it working.
Yeah, so yeah, because what will be interesting is to integrate it with, as I mentioned yesterday, with the media server like Janus to be able to distribute it. I mean, I guess that could also be a part of Link server as well. But
Yeah, but you can also connect through UDP and others, not necessarily WebRTC. WebRTC is just a possibility. But of course, the signaling needed to take care of. And it's open source. If you want to change the signaling logic, you can add it. And you can add the Janus signaling if you wish to. It's like nothing is holding you to add that.
Mm-hmm. Yeah, thank you.
Well, if that's all, thank you, everybody.
All right, it looks like the bentos have arrived. So, take a few moments or a few minutes to go grab a bento if you want one, and then we'll restart the talks in 5 minutes or so. Hello, hello. All right, please make your way back to your seats if you can. Is this your coffee? Here is a water, if you need a water. Little sound test, sound test. Sounds okay?
Yeah.
You'll do a quick intro yourself, right?
Oh, yeah. Yeah.
All right, final call. We're going to start the next set of speeches soon.
Start singing. Like karaoke. Yeah. Oh, give him a minute. Let him settle.
It's for you. It's not for anybody else.
Okay. All right, folks, I will get started. So this is our lunch slot for the presentations. My hope with this talk is it's entertaining and a bit light. So yeah, I'll introduce myself. I'm Nathaniel. I'm a kind of adjacent to ArduPilot in my regular work, but I've relied heavily on ArduPilot over the years, and I've really grown to love it and used it. And now at this point, I'm starting to become a small-time contributor too to the project. So yeah, my talk today, I really want to focus on one of my main outputs for my work with ArduPilot, which is around using ArduPilot Gazebo to do prototype design for our aircraft systems. So a little bit about me first. Can I just hold this? A little bit about me first. I'm a mechanical engineer by training, and over the last 8 years or 9 years, I've tried to pivot more into robotics control and systems. So in my research work, I've really done my core focus on reinforcement learning, optimal control, multi-agent swarming systems, and engineering design. My day job is I'm a engineering manager for the company I work with named Romeris. And what we're trying to do is develop a new type of plane UAV system based on hang gliders and air trikes. And I'll explain a bit more about that pretty soon. My PhD work centers around my work with the company, where we've developed a world first adaptive flight control for these UAV systems. And just to call it out, this is my 7th year now of using ArduPilot for my development work. When I started, I really didn't have a clue what I was doing. I wasn't a classically trained software developer, so there was a steep learning curve to pick up how to program real-time systems with C++, especially for control of, flying systems. So yeah, it's been a long road. That's me there with my my Hexoon TD900. My other activities all these days kind of center around tech development. So just calling them out because I think if you have any interest in collaborating after the fact, I'm a program coordinator for a training initiative at a university in Ottawa, where I'm from. I'm a technical lead for a consortium where we're trying to work out how to do greenhouse gas emissions detection using drones and correlating that to satellite data. And we're looking for new partners for that. So if that interests you, please talk to me afterward. And recently I got offered a small-time tech fellowship role with a venture capital startup incubator in Montreal. So I have a bit of reach now, which is nice for my work. With respect to my work with ArduPilot more recently, just to call them out, we've done work now doing greenhouse gas emissions detections where we mount a methane sensor onto a drone and we fly patterns to try to characterize like gas plume distributions. So that's one example there. And then for some more recent development work we've done for ArduPilot, we're trying to take the bendy ruler avoidance algorithm scheme that was used for the Outback Challenge in 2018. And we're trying to convert it to use more like a Lua scripting framework. So if you're familiar with like the ship landing feature in using Lua, we're trying to use that as our example to start with and then build out the old plane avoidance features using bendy ruler as a Lua script or a set of scripts. So at this point now we have the obstacle generation working. We can communicate between ArduPilot and Lua to discuss obstacle state. And we're able to see if there's clear to proceed versus if there's an obstacle in the way. And now we're trying to work out how to do the actual avoidance calculations and control using Lua. And so that's what we're working on now. Okay, so to my development work, this here is our electric unmanned weight shift control aircraft. So when I say weight shift control, I'm talking about like hang gliders or air trikes. So completely different than the normal fixed wing planes that most of us use for ArduPlane. Why these? It's just flat out, no one's done it. And we think that they have some pretty interesting qualities that are worth developing for or to use eventually. So they're extremely low cost. They're extremely low maintenance. They have long range, being a larger plane, and high endurance since they're a glider. And you can also maneuver them at low speeds thanks to their weight shifting control and the large kite wing that is on top. The challenge with these aircraft, though, is it's very difficult to model a flight control, partially because nobody's done it. And the aircraft dynamics themselves are quite nonlinear. So let me explain what I mean by that. These aircraft, like I said, they don't have control surfaces. It's a big kite, and you're shifting your mass underneath to try to change your attitude. And you're moving your mass sitting in the seat under the wing in free space. So you grab the bar, and you're literally doing like this. So it's a completely manual control. There's not yet fly-by-wire systems to control aircraft like this. They just flat out do not exist yet. And part of the challenge that the company perceives, company being Ramirez, is it's tricky to learn how to fly these as a pilot. So even if you're an experienced or seasoned fixed wing pilot, when you then go and try to become a weight shift pilot, it takes tens or 100 hours just to convert your pilot brain from fixed wing to weight shift fixed wing. And a lot of it is fly by feel. Putting that in a technical way, there's substantial time delays to the control, and you have to be precise. So you can't be too slow and you can't be too fast. You have to be just right, to put it in a fuzzy sense. Flying these is a lot like driving a motorbike. Like you have to kind of lean into your turn and then lean out to turn correctly without falling over. And that's actually a challenging control problem. So just to drive the point home, here's an example of a banking turn. Your pilot applies a force on the control bar. you shift your whole mass under the wing one way, and then after a couple of seconds, the wing starts to rotate and you initiate a bank. It's a bit more complicated than that, but that's the basic idea. You're creating an imbalance that causes your attitude of your wing to change, and then you have to get yourself out of that changing imbalance that you just started to put yourself back into a balanced state or a trim state. So our development, it was tricky. It's like, no one's done this. There's no hardware for it. There really isn't much literature on it because no one's done it. How do you start? And so we have experimental and shop efforts, but part of the problem is it's expensive. We can't take a big risk you normally could for prototype development because we're not quite sure how to do it and we don't want to wreck our wings. And in the case of manned aircraft, we can't put the pilot in harm's way. So one idea was, obviously, can we use simulation to replace flight testing and development? And the answer obviously is no. You can't just simulate your aircraft and say, yeah, that looks good, it'll work in real life. You just can't match everything that reality will throw at you. But it does present an opportunity, which is you can refine your models as you go over time to try to get closer and closer to real life. And what I really like about this approach to like dynamics simulation is you're not so much worried about a top level design, trying to just say, do exactly this. Rather, you're trying to come up with all the ingredients or pieces of your dynamics environment or the models that all work together. And through their interactions, you end up with something more complex or sophisticated. So the flight dynamics in the case of our weight shift models is sort of an emergent property of our approach to dynamic simulation. So if you're familiar with Gazebo, it's de facto the most used open source dynamic simulation for roboticist. But most of the time they use Gazebo for ground robots or stationary like multi-link robots. It's not as commonly used for flying robots. But what's really nice about Gazebo as like a developer tool is it's open, it's extensible. And with the recent upgrades they've done to their newer versions of Gazebo, the software architecture is far more modular than it used to be. So how I understand it as a mechanical engineer who does a little bit of development using Gazebo is the newer version is much more easy to support over time and use than it was 10 years ago. So as an example, if you haven't seen this, I strongly recommend searching this after my talk. But the ArduPilot community has done work on using ArduPilot CIDL with Gazebo. And so in a nutshell, you use lockstepping to make sure your Gazebo environment dynamics are in step with your flight control CIDL simulation. And this kind of gives you a way to actually do more sophisticated simulation than you otherwise could with just ArduPilot CIDL on its own. So this is from the ship landing demo page. So it's really cool. In a nutshell, they use a VTOL and they fly around a boat and the boat's rocking on water in simulation and they try to land it. And there's also some communication between the boat, which is running ArduBoat, and the VTOL plane to kind of coordinate at least the orientation of the plane relative to the boat. So in my work, I ended up contributing this model for a weight shift aircraft or an unmanned weight shift aircraft, UWSC for short. And it flies just with base ArduPlane. There's no additional control sophistication required to get this model to fly. And what was especially nice about this work is we were able to validate at least the dynamics that the aircraft model is approximating with real flight data that the company was gathering from manned recreational flights. So we were putting a, here.
Well, before that, I just want to say if Reese is listening, special thanks. He really helped out with this work and kind of helping me get up the learning curve. And not only that, I think he's been kind of the sole Mac OS Gazebo developer guy the last few years. So big shout out to him if he's listening. And if you know him, tell him I said thanks. Yeah. So yeah, it doesn't seem all that impressive as a picture, but this is the first time anyone ever has implemented a navigation controller for a weight shift aircraft. Like, it doesn't exist until this. So yeah, in a nutshell, we're using the L1 and text controllers. We're driving state information to pick general reference angles we want to hit. And then we're relying on just the feedback to actually fly the aircraft. So it plugs right into basic ArduPilot. I want to stress that point. You could try this today if you want. And what's important to highlight is, unlike the fixed wings with control surfaces, the tricky part is our control has to move a pendulum swinging underneath the wing in a certain way. So it's a little more tricky from like a dynamics perspective than what you would normally just say, here's my model for my control surface. And if I do this much command, I'll get this much response at that speed. So just before we get too into it, just a little video break. I wanted to pull this up just to show an example of like a city environment in Gazebo. And we're flying little planes, like a demo mission using Gazebo, or maybe you have some visual sensor of some kind. So then here's the unmanned weight shift control model moving the pendulum underneath in roll, then in pitch. One of our validation missions. So we took 13 sets of mission data and we said, hey, try to fly roughly that track. And let's try to compare the dynamics that come out of that. Or not the dynamics, sorry, the logs that come out of the simulated mission and compare it to what we got from our real life avionics. Here's some new work we've done for our greenhouse gas consortium, trying to just demo, hey, if we put a sensor in Gazebo, we read a gas cloud as we fly through it. And so, yeah, you get through the cloud and you get a little spike. Here's another one. We have multiple aircraft all flying at different altitudes to try to say, how does the gas measurement change as you go away from the emission source? And lastly, here's kind of the long-term vision. If I have a whole bunch of really cheap planes with long range, with gas sensors, can I just drop them into an area of operation and coordinate their flight to characterize whatever's going on in the area of interest rapidly? So that's kind of the long-term vision I have for that work that I'm trying to do. So each of those lines is a trajectory being drawn by a plane. To the presentation. Like I said, we flew real flights and we put ArduPilot on the aircraft in just like a monitoring mode. And we collected we collected logs from the flight. And we used that to validate our simulation model's accuracy. So here's one sample. We actually track quite close in both the altitude and the 2D ground track projection. And that held for the majority of our missions. Here's a comparison of parts of the 13 flights all put together. So a level section and then turning sections that we defined, just to show, hey, yeah, whenever we have these two parts of the flight that we care about, how well do we track them? Landing and takeoff. So you can see a divergence here. In the case of takeoff, since it's automated and simulated, the takeoff is like perfect each time in Gazebo, whereas in real life, there's variance from the human pilot. And then for landing, different problems. The landing approach depends a lot on just how the pilot decides based on the wind conditions to descend and then slow down and touch down. And then using Gazebo lets you do crazy stuff. So in my work, my primary focus for my PhD project at the beginning was implementing an online reinforcement learning scheme. I won't get too much into it, but in a nutshell, the controller I'm really proud of takes a simple combination of dynamic stability and tracking error information and combines it together into a set of information that then your online reinforcement learning learns against. And this online reinforcement learning algorithm is implemented directly on the flight controller, on a Raspberry, or sorry, on a NavIO, or a Raspberry Pi with a NavIO too. So doesn't take much. And the reason that works is because we're using something that's not super commonly known called temporal difference learning. And it's based in a type of theory called approximate dynamic programming. So I just wanted to call this out because I think there's a lot of attention on learning where you need a big heavy GPU and a computer and offline training and like 100 hours on a stack. And these methods are meant to be used in real time. So you could incorporate a learning agent with your control to try to suss out some particular behavior that eludes you. So with reinforcement learning, I just want to be clear, it's not a magic bullet that just does control better, nothing like that. You really use reinforcement learning when you want to try to do more than just solve an error. So if you're trying to balance multiple objectives like, hey, I want to keep my airplane in the air, but I also want to try to track error somewhat. So like, here's an example. We put an experienced pilot on the sticks in simulation. And on the left side, you can see this is their roll track. And on the right is the evolution of the agent weights for the roll controller. And it flies okay. It tracks well enough. There's saturation conditions that we try to avoid, but as you can see, it exceeds them and then comes back. Saturation limits on the roll state that we want it to be allowed to have, but it keeps the aircraft in the air and follows what the inputs are. Meanwhile, for our pitch agent, the other controller, because we only need roll and pitch to fly these things, it kind of learned pretty quickly, hey, don't follow the pitch reference angle the pilot's giving you. It's junk. There's a limit on it too. So instead, I'm going to try to just fly this thing and take the pilot's input as a suggestion, which sounds weird, but I remind you, the whole point of reinforcement learning is not to solve errors. It's to just balance multiple objectives. As long as you can define what you mean by an objective mathematically, you have data, maybe you get a result. To the real meat of the presentation. This last year, we had a really big challenge, which was, God damn, it's hard to actually develop prototypes of full size 100 kilogram plus aircraft that are unmanned. Big challenge. We're not at that scale yet. So we pitched, what if we made a miniaturized version? No one's done this. The closest is there are RC models, but the RC models don't have formal analysis, and there sure isn't ArduPilot solutions for those RC models. Or if there are, I'm not aware of them. So now we've done that. Again, I just want to remind you, part of what makes flying these aircraft difficult is you have these air elastic properties of the wing that kind of dictate how the sort of the aircraft responds as it flies and changes speed. So yeah, the challenge was, how do we scale this to different scales? How do we make unmanned weight shift control aircraft at big scale and at small scale and in between? And thankfully, because of the simulation framework we developed using Gazebo with ArduPilot CIDL, it really helped accelerate our prototype development. So just to remind you, you define your geometric, your mass, your inertial properties of your aircraft. To size the wing, we used a program called XFlyer5, XFLR5. And then based on the aerodynamic results of XFlyer5, we tried to map it to the really rudimentary lift drag plugin that's in Gazebo. We sized the pitch and roll actuation to try to match our real servos that we were using for the prototype. And finally, we put ArduPlane on it. And we just followed the ArduPlane default setup process. There's no other tweaks. The closest thing to like a tweak would be there are things you have to do to the parameters slightly differently to get it to fly more like a weight shift aircraft compared to like a fixed wing. And doing that, you can get a prototype that flies pretty okay. I think there's work left to be done on trying to say, okay, what other adaptations to the control do you have to do to support different parts of the flight envelope for your weight shift aircraft? But good news, if you don't mind having a highly performant aircraft, you just want it to fly at like low roll and pitch angles and reasonable speeds, you can pick a set of PID gains that works and you should be set. So yeah, back to the development of our prototype. The initial maiden flight of our aircraft was based off a auto tune in Gazebo. So we took the model, we auto tuned it. We said, okay, what did it spit out? And then we said, we're kind of scared of some of these parameters it spat out. So how about we make them a little bit more conservative or weak? And it flew fine, not great. And we could keep it in the air though, which was impressive on our first attempt. We kind of developed what we called our input replay script. And the basic idea is we took the literal RC input from the pilot and we just fed it back to Gazebo, trying to match it to real time. And really crude, it needs more work, but that's what you're seeing here is the RC input of real life to simulation. This method will work, but to a point, because as you continue like your simulation of your dynamics, eventually what you simulate will diverge from real life. It's just a fact. It's too hard to match things precisely unless you have an excellent model and really good feedback control to keep it where you want it. So here's like an example from our first maiden flight, comparing it to then a simulated version of the maiden flight. So I want to really highlight or stress that we're not, the only thing we're giving the sim is just the RC inputs. Otherwise, the sim model is just doing what the RC input says to do. And yeah, it follows the dynamics reasonably well. So like speed, same shape, different magnitudes. Altitude is almost perfect, which was nice to see. And then pitch and roll are pretty close. The roll looks kind of funky, but that's only because, sorry, the top right one, that's only because the roll angle in real life went over 180 at one point. Here's one example that was really fun. We did one flight test of our prototype and we flipped it. We took off, we put too much throttle on it and the thing flipped. Not great. And so the question we were sitting around scratching heads and it's like, what did we do? Like, why did it flip? We haven't flipped it before. We've done the takeoff kind of the same each of our flight tests, but that time we flipped it. Were the wind's bad? And our hypothesis that we were working with was maybe there's just too much throttle. Like maybe the throttle is oversized or the thrust, sorry, and the pilot used too much throttle. So instead of kind of head scratching, doing some napkin math and then trying it again in real life, we said, how about we test it in simulation first, just to confirm. And sure enough, we do input replay and we're able to match the dynamics of the flip. For me, it was a shock. Like, I didn't think the crude lift drag plugin in Gazebo could do stuff like that. I thought it would just say, oh, you're fine, keep climbing. Like go pitch up more. So yeah, satisfying to see. So that's like a front view and that's a side view of the same loop. And they line up pretty well. So then we say, well, let's just drop throttle, put a limit on it, see what happens. So now what you're seeing is a before and after. So before is our previous figure of the two loops in sim in real life. The after is the simulated loop if we apply the throttle limit. And what do you know? It takes off and it kind of floats and then it hits the ground. Great. If we had done that, our flight test would have been great. We wouldn't have done a flip and hit the ground. So we did it. That's what we did. We put that in real life. And what do you know? It saved us a whole wasted day of flight tests, damaging our aircraft, having to repair it. So the cost saving, both in like time and money, is immense. So yeah, I can't talk too much about the development, like the flight test campaign from this year, but it's been very successful for us. We've gone from a simulation model that we cooked up in November of last year. And this summer, we've gone to a point where we have a totally novel prototype of this aircraft flying in auto mode. And what we're trying to work out now is how to do auto landing and then auto takeoff. And if we can do that, that's a workhorse. We can probably go do revenue jobs with it. We can go show it off. So I want to really stress to the room of developers or interested parties, I think the use of Gazebo or equivalent dynamic simulation with ArduPilot remains untapped. And I understand part of that is there's a steep learning curve and the utility of it might not be clear. But for us, what it's provided us is an essential tool to make our development more rapid. And that's because it gave us a way to do initial tuning. We can do post-flight analysis using simulation. And we can even consider different case studies in sim rather than in real life. And so yeah, on the left side there, it's just from last week. We did an auto mission and then an auto land attempt. It's hard to see on this. I don't like that. I'll post it in Discord later, but I'm really proud of that image. It flew great. Our L1 controller needs tuning, but it tracked the waypoints, it kept altitude, and then it almost landed really well. And if you've worked with auto landing, you know it's a little tricky. So, so video break number 2. Just a little demo reel. Here's the full-size prototype we developed a few years ago. Before we ran into the challenges of how are we actually gonna get this thing to fly autonomously. Here's a equivalent prototype floating, doing state regulation. So I want to show that a bit more. On a beach in Mexico, and we're basically just letting it float off wind coming from the ocean, and ArduPilot is controlling the robotic actuators to kind of keep it still in space. Here's it rolling. This is from promo footage I don't care about. Looks cool though. And then here's the miniature prototype I was telling you about flying in the air. So I'll just let it play out. Here's FPV footage from underneath at our test track in Ottawa. The overhead pass. A for this one. And then here's another overhead pass in fly-by-wire B. So it's way off in the distance. The pilot's doing visual line of sight control, but it's in fly-by-wire B, so all he's really worried about is just altitude management and heading control. Whoa, sorry guys. What am I doing? Oh, shoot. There you go. That's real time. And yeah, it's flying like a charm, just with base ArduPlane. So yeah, to come back to it, I just want to say thanks to Randy and Andrew or Tridge for inviting me to come to the conference. It's my first one. And then for the hotel staff for their hospitality, and for Kaga City for welcoming us and letting us enjoy our time here. And yeah, I have a few calls for collaboration. There's a whole bunch here to give them rapid fire. If you want to work on simulation-oriented prototype design work, that's kind of my bread and butter now. Provide data on drone delivery methods, or you have a connection. We have students at Carleton that really need help with data access. So if you know anybody, please do me a solid and come talk to me afterwards. You have room in the utility program, the training initiative I mentioned, for international partners. It's winding down over the next year and a half, but we're trying to think about what comes next. That's kind of the spiritual successor. So now that I'm hooked up with you lovely folks with ArduPilot, I'm hoping to find partners for that. We want to start exploring wildfire management projects in Canada. We're already doing science mission payloads through the NRC, and we have the Greenhouse Gas Consortium. So if you find that work important and you want to work with a satellite data provider from Europe, we have the connections. And then finally, looking forward, we're trying to develop detect and avoid systems that are low cost using sensor fusion methods. So that's to support our beyond visual line of sight development that we're trying to get up to. So if you're interested in any of those, please don't be a stranger. I made these cheesy little cards just for this. So come on by, say hi, and let's chat. Thank you. Questions? Yeah.
Fantastic talk. Thank you.
Thanks.
I was curious about what this vehicle would be like to fly in manual mode with RC, where you don't have the feel, the feedback in an aircraft like this. I've never flown anything like this. I've never flown a hang glider, but I imagine, like you described at the beginning, where the feel of the aircraft on your body is very important.
Yeah.
So have you done much flying of this in manual mode with radio control? And in which case, how hard or easy is it to fly in manual mode?
Okay, so I left it out because I wanted to focus this on unmanned applications. But the earlier development with Ramirez was really on optionally manned actuation systems. So how do we do a fly-by-wire system or a robotic system to replace a human pilot? Basic math there is you take the pilot out, you put in stuff. You can do more with it. But the CTO of the company is a weight shift pilot himself. It's a hobby for him, really, the company. And we're trying to build a whole company around his hobby. So why I'm mentioning that is most of our bandwidth early on was just, how do I make the fly-by-wire system give feedback? How do I make it feel so that I can sit there on the sticks? And the fact is, we don't have a way right now to give tactile feedback. So what we've had to do is develop force admittance systems for the full-size aircraft. So in other words, like a cable-driven robotic scheme that lets you vary the amount of force you apply to be a soft touch or a hard touch, depending on if you're in a really bad state and you need to get out of it, versus if you're just trying to do a control and to remain gentle. And so doing that with like at a force control level has allowed us to give the RC sticks to a trained shift pilot and fly it. And so that's been our proprietary work on the actuation systems itself. But that wasn't through like an unmanned application yet. So then the other side of it is our work with the this one, the M2, or sorry, the miniature prototype. And the fact is, when we first made the prototype and we gave the ArduPilot control in manual mode, no less, not fly-by-wire A, and we said fly it, it was bad. He couldn't fly it well. It was hard. Part of the challenge is just like I mentioned earlier, you're not controlling control surfaces with a very quick response. You're controlling a big dumb weight and you're trying to jostle it around to keep balanced. So it's like a mix of an inverted pendulum and a motorbike, right? So manual mode, kind of crap. Maybe if you really get skilled with it, you could learn how to fly. But we said, no, this is stupid. Sorry, this is silly. Let's go to fly-by-wire A and try to rely on the built-in aero controller. And yeah, it flies pretty okay at limited parts of the flight envelope is the key. So we're not trying to do acro flights like what Andy was showing us yesterday. So is that roughly what you were looking for?
Yeah, it's sort of what I expected. And it's because one of the things that I would often do with a new aircraft is I would try to make it trim the aircraft so that it does fly reasonably well in manual mode and then apply the automation on top. But I was curious as to whether that methodology would work at all. And it sounds like it doesn't work well because flying it in manual doesn't give you the feedback you need.
No, so it could work if you had a really well-balanced and well-designed version of this prototype. So going back to the full size, the difference between a real cheap, like $10,000 one and like a $100,000 air trike comes down to make or quality of the build. And they put a ton of attention into wing balance and weight balance. And I know any aircraft system, that's what you care about, or plane system. But especially for these aircraft, if you don't balance those things well, that's the difference between a really nice, relaxed flight and a flight where you're sweating and you're working like you've never worked before. And if you don't hold on, you're gonna lose your strength and basically fall out of the sky. So that's for manned pilots flying manually. And so the challenge is really, part of it is prototype design or aircraft design, just making a good aircraft that's balanced well. And the other hand of it is, hey, can you rely on automation to make up for a poor build, which this, as nice as it looks, isn't very good. It's a first attempt. So yeah, I think if you invested to develop a good version of this, you could probably use that approach. And then it would just come down to setting up your sticks right so you can provide gentle control. So you don't put it into dangerous parts of the flight envelope. Like, to finish the thought, when I said this, there's a real stress on us, like being patient with your control, but not too patient. It's a challenge of finding the right rate that you apply your force input, not your position. And when you let off the force input. And the difference there is that's like a really bad like S-curve heading control, or a really slow, steady, oh, this is great, I'm flying great, until you do this, and then you're sideways. Like that. So, yeah.
Thank you.
Thanks. I guess wherever the microphone goes is whoever gets it first, so.
Can you speak to setting up Gazebo for a novel vehicle like this? Were you able to use your mechanical engineering knowledge and set it up easily using information for more typical vehicles, or was that a challenge to convince Gazebo to do what you need?
No, it's just a bit of a learning curve. But if you're patient and you have time, it's pretty easy to come up with like your inertial model and your geometry model in Gazebo. Like through the SDF format. And then at that point, it's just setting up your, how it moves through space well. And then there are challenges with Gazebo. Like the primary issues with Gazebo is it does decent physics simulation, but it falls apart when you want like good friction models or like contact models between parts of your robot. So it depends on your application. But as a mechanical engineer, if you're trained and you understand this stuff, It's just a matter of trying to figure out how to convert it into the mathematical description for gazebo.
So with reference to your comments about flying on stock ArduPlane, where did you mount the flight controller, or specifically the IMU?
Where's the IMU? It's on the wing.
Okay.
Is that what you're asking?
That's
bro?
exactly what I was
Yeah.
asking.
So in fact, if you really think about it, when you're flying these bad boys, you're not flying the fuselage that moves underneath, you're flying the wing. So as long as you don't even really care what your fuselage is doing for the most part, you just want it to move your wing correctly. So my core research work from when I started before I became a drone engineer for whatever reason was on the learning system stuff. So this is a model-free control like ArduPilot, and I don't really care what the weight shift is doing when I'm controlling this with this controller. I just want the wing to stay up and stay stable. So what really matters for this controller design is sort of how you couple the information of the dynamic stability the reference dynamics with the IMU error or state error from the UKF, and then to control the wing. Thanks. Geez, busy crowd.
ありがとうございます。すごくリアルタイム、リアルと、シミュレーション、すごく興味あるんですけども、私は PC で SITL を動かす、SITL ですね、動かすと、OK、Not フライトコントローラーだと BAT という経験をしているので、今、シミュレーションオンハードウェアを使ってテストをしています。で、もしそちらの方でシミュレーションオンハードウェアでの確認等されていたら、その辺のことをお聞きしたいなと思ってお聞きしたいです。以上です。
So you can't put the translation there. It's only going this way.
It's not good?
Well, look.
It seems like it's good, but okay.
Did it tell you what he said?
Roughly.
Oh,
He doesn't care about real life. He only cares about games, which is a sentiment I can appreciate.
No, I think it doesn't work right. Actually, it's set up to go English to Japanese only, so it doesn't.
Oh.
It doesn't go back the other way. It does not.
Oh, so this is cooked.
Yeah, sorry. So I think his question was that in his experience, he has tried to tune in Siddle and then run it on a real vehicle, and it has not worked. And then I think he said that you've had better experience running Siddle on hardware, and
So like a flight controller hardware that's plugged into a simulation environment?
I guess so. Is that correct?
Don't ask.
もう一回最後の方、なんか、ハードに、なんかフライコンにシミュレーターが動いています。
そうです。私は、キューブオレンジプラスにシミュレーションオンハードウェアをインストールして、自分の作ったプログラムをテストしている。
Yeah. So he is running simulator on a Cube Orange plus light controller.
Yes.
And そっちの方がうまくいく。
Yes.
And he thinks that works better than running it just on your PC.
As software, okay. Yeah, I haven't done that yet. I have my flight controller running next to my computer and then communicating. But I don't see why that wouldn't be the better choice for the flight controller side of the simulation, right? Like, to come to it, like at the end of the day, Gazebo doesn't care where your inputs are from. You just need to provide it input. So yeah, I haven't ran into issues with my flight controller software running poorly in simulation, like in Siddle. Really, my focus has been on the dynamic simulation side. So I want to highlight this slide here. It's a philosophy. It's saying, can I use simulation to replace real flight testing? Of course not, no. But if I refine my models over time as I collect more data and I improve them, eventually I'm going to come up with something that's closer and more useful to the real one. So in some sense, giving your dynamics simulation access to real flight controller hardware is probably the better choice, because it's what you're not modeling anything anymore. It's just the bloody real thing. Like, just use it. So I think that's a good approach. Is that a satisfying answer though?
Thank you. ありがとうございます。
No problem. My pleasure. I think there's two. There's Michelle and then one in the back.
Running a little short on time.
Yeah, I'm a whole hour almost. You're making me work, Randy.
Last question, Michelle.
So I was just wondering, because the manned ones are quite mechanically complex, whereas these ones, I was wondering how you did the mechanical part of it, because servos, I assume, would be not strong enough.
So the full size and the miniature have kind of two different development tracks for actuation. In the case of the full size, I didn't talk about it, but we can talk a bit more after if you like. In a nutshell, I used it's called a cable-driven parallel robot to provide me with like flexible admittance. So it can be stiff when I need it, or it can be a soft touch when I need it. And I find that works well for the large volumes of the full-size aircraft, rather than like a fixed link arm, which would be very hard and expensive to design for the application. So a cable-driven robot, if you think of like a sports stadium, like a camera gimbal set up on like big cables, it's basically that. And I can do that with just a set of like 4 actuators. So it's very cheap. In the case of the miniature model though, I cooked up this, you can't see it, but it's like, I call it a servo hang block that replaces the hang block. And it's an okay design. It definitely isn't the right design for the miniature, but the challenge is picking the right actuation scheme for the scale. So as you scale up, the servo hang block design that this one uses definitely would not be a good choice for the full size, because you would need some crazy big and expensive servos for the small volume of the hang block. The hang block being the thing that joins the wing to the fuselage mass. In the full size, I'm using a cable robot. So in other words, I'm using different actuation schemes. And then what I'm trying to do is map my adaptive control action to be agnostic to what actuation scheme I'm using. So I don't care what actuation scheme, it just has to fly kind of the same, despite the scale difference. And so that's what this shows, is an adaptive actuation scheme on the simulated version of aircraft.
Oh, thank you.
My pleasure. Okay, you want to wrap it up or do one more? Okay.
Testing, testing. Did you turn your speaker off? Rishab, sounds okay on? Yeah.
No, speakers off, it's the microphone.
Yeah, it's your microphone should be off and your speaker should be off. Yeah, but that's for going in. You also have to turn your speakers off. So like the sound, so you can't hear anything on this. Yeah, it looks good. Testing? Yeah, that's good.
Thank you.
It'll take a couple minutes. Sections. All right, we're going to start the next talk soon, so please take your seats. Seats, please. You go get them.
Well, the ones in the room are fine. It's the ones who've wandered outside.
Yeah. All right, we're going to start now. So everyone, please take your seats. No, we can't. That's when the Ethernet went off yesterday. Hey, Kawamura-san. Kawamura-san. Katsumata-san. Katsumata-san. Minasan. Nantoka. Seki ni modoshite kudasai. Or something like that. Okay, I think you just start. Okay, bye.
Yeah, good.
Can I have everyone's attention, please? The next presentation is starting soon. Please be seated.
Minasan, konnichiwa. Wa nashino nameo, Tim the Plane Man. And welcome to Plane Time ArduPilot Developer Conference, Plane Follow Edition. So a few weeks ago, before the conference, I believe it was about the 8th of October, I did this. And this isn't, well, what's going on? Oh, see, it's okay. Oh, no sound. It's a shame. And by the way, if I didn't mess it up, but if you watch it on your computer, you might find you get a better view than watching it on the screen. But if you can see, we have two planes. They're two mini striver, about 2.1 meter wingspan VTOL planes. The first one is flying an auto mission. The second one is autonomously following it around the sky. I have two pilots there. I'm actually piloting the second plane, but all I did was flip a switch. And it's pretty amazing. So here's the view from on the plane. This is on the second plane. And if you can see in the right-hand side, there's the first plane coming up in the air. It's just coming up right there, as you can see. And again, that is just completely autonomous, telemetry driven. The little black thing you can see sticking up here is a SIK telemetry radio from Holybro, and I have two of them. They're running at 500 milliwatts, one on this plane, one on the other plane, and there's a direct telemetry link. So MAVLink is coming from that lead plane and feeding to the follow plane and feeding global position int and attitude messages that the second plane is using to figure out what to do so it can follow that plane. Again, it bears saying because it is important. I mean, we're ArduPilot, but that what it's doing there is detecting that the other plane is turning, and it's deciding to turn. The other plane is going to do a turn to the left a little bit, and it decides to go a little bit further to the left, and then the other plane will turn to the right to head off towards the field where the pilot location is, and again, now it's figured out that it's turned. Of course, there's a little bit of a lag, and that's one of the challenges to deal with in this situation. But it's basically, it's doing it. It's doing it, plane follow. So to my slide deck for a second. I didn't realize this, and I'm sorry about that. But when I play the deck, and so when I play the deck, I guess I lose everything else. So I may have to do that, and because I do want to flip back and do a couple of demos on the way through. So what happened was that about 6 months ago, maybe a little longer, Hexoon, and thanks Phil and Sid, sent me a EDU 650, and one of the things that I wanted to do with it is try out the copter follow me mode that I saw at last year's ArduPilot Developer Conference. So what happened was I set that up, and I did a video, and I posted that on my Tim the Plane Man YouTube channel. And the very first thing that people started to do was, well, that's great, Tim, but can't you make it work with a plane? You are Tim the Plane Man after all. So the challenge accepted, I started having a look to figure out how I could do it. Of course, those of you who know realize there is no plane follow mode in ArduPlane the way there is in the ArduCopter. And so, but there was a fairly rudimentary example Lua script in the GitHub under AP scripting libraries examples. And I pulled that down, fired it up, and did a little CIDL demonstration of getting it to work. And of course, the first thing I found were challenges and problems. So I did a video, and I did a CIDL simulation of plane follow. And the next thing that happened was I got a big break. A company from Australia called AirGeoX contacted me. And what these guys do is magnetometry surveys of outback locations in Australia. And they send up planes like the Striver Mini into the sky with big magnetometers dangling below them in this case, and survey vast swaths of open area, fundamentally looking for gold. They're looking for the magnetic signature. Well, they're collecting the data. They give it to a geologist, and the geologist looks at it and said, oh, yeah, there's probably gold over there. And these guys have actually found gold, and there are now, there's a new gold mine, for example, near Tennant Creek in the middle of Australia, which is where I was born, that is now mining gold at a location identified by the ArduPilot powered mini striver flying around that these guys do. But they said to me, listen, what we want to do when we go out and fly these things, we want to be able to fly 2 planes, or maybe more than 2, but 2 to start, because we want to have the 2 planes, as far as I understand it, fly kind of at the same time. And they want to fly them in parallel, one next to the other. And they don't want to have like 2 planes set up with independent missions where they'd get out of sync and they'd lose time synchronization. They literally want to have them fly together in parallel across and gathering the data on both planes at the same time. So they said to me, listen, we'll give you some money. We want you to build this CIDL thing that you've done and make it work on real planes. And so got stuck into it. These are the requirements. So first of all, the lead vehicle gets configured with the survey mission, but you don't have to configure anything on the follow vehicle. The ultimate target would be that the lead plane and the follow plane follow each other about 25 meter separation, but not behind or ahead, but in parallel, literally side by side. Someone who I spoke to earlier was asking about how that works. And the simple answer is that we use the same follow parameters that Copter uses. And one of the things that has is X, Y, and Z offsets. So you can simply say, follow this vehicle, but follow it 25 meters to the right, Y equals plus 25 or minus 25, X equals 0, so 0, 0 neither to the in front or behind, and requirement is around altitude. They don't want the second vehicle to follow the altitude. They want the second vehicle to have it to follow the terrain. Because of the surveying they're doing, they both want to fly about 50 meters above their own terrain, which could be obviously different if they're a certain period apart. So they shouldn't be flying a coordinated altitude. They should be flying above the terrain. So thus started my plane follow project. Started by ordering 2 mini strivers and then building them and maiden flight and test and getting them to fly. I call them the Lyapunov and the Brolga. Good Aussie names for Lyapunov is sunset in some native Australian languages, and Brolga is a fairly elegant flying bird that has some interesting dance behaviors in its mating patterns. What I did then was improved the simulator. I spent hours and hours and hours and hours running CIDL and got the simulator to improve. Then I flew on a real plane, and an interesting use case, a real plane following a simulator. So I simulated a plane flying around the sky, and then I threw a real plane and had the real plane follow the MAVLink feed of the simulator. Everyone but me thought I was just flying one plane, but I was actually flying 2. One was virtual. And then it was, once I got it working with my little foamies, that I didn't care if it crashed or whatever happened with, and I got some of the bugs out, went ahead and did it with the real VTOLs. And then eventually I got to the video that we saw a little bit earlier, where the planes actually follow each other around the sky. And of course, it was, lots and lots of iterations of improvements. So what I want to do now is, again, I just flipped out of the video, I guess. I'm going to switch to a slightly different video here. I can get to the window. This one is not the original CIDL, but it's the new improved version. It's a fairly recent, I recorded it a couple of days ago. So it's the almost version 1 finished version of CIDL. Vehicle 11 is the lead vehicle, and vehicle 12 is the follow vehicle. It's using one of the main pieces of inspiration I got for some of this stuff was the dual plane aerobatics work that Tridge did and demoed, I believe, at the last year's conference. And so if you have a look at the code, you'll see I harvested lots of the stuff that he did, and in particular, the ability to have to simulate 2 vehicles sending messages to each other using MAVLink was very, very helpful for this. So here we have the vehicle. It's doing a turn, and if you can see it, you can't really see it on the screen so well, but if you look at the yeah, okay, I'm going to try and stop that somewhere where you can actually see the. Can I get that to not pop up? Oh, there we go. Okay, I'm trying to use my mouse to point, and as soon as I put my mouse over the video, it pops up the controls, which I don't really want. So I used 2 ways of navigating the plane. Simulation, and also there's an example of swarming in Mission Planner that tries to do follow, especially in plane, by just dropping a location point ahead of the plane as it flies around. And that works great when the plane's a fair way ahead. But it won't work when you get close. If you can imagine, if there's a plane down there and it's a meter to the right of where you want to fly to, but I'm still flying towards it, I'm pretty much doing okay. But if the plane is right here, if the point where I'm targeting is 1 meter to the left or 1 meter to the right, the plane here is going to be flopping around all over the place trying to hit that target point because I'm right there. So what I do, and this is where that the dropped point that you can see in the map, as it flies, it keeps losing it. If you notice, it'll drop to the point, but when it gets close, that point will stop happening because I'm switching into guided heading mode instead of guided do reposition follow mode. So when I get very close, I actually follow the heading of the target vehicle, and I adjust my position by adjusting the airspeed and not by trying to target the roll pitch yaw direction of the aircraft. So if you watch that, you'll see that that's what's going on. It's dropping that little point. When it gets really close, it forgets the point, which CIDL just leaves on the map, or MAV proxy leaves on the map until it decides it needs to reposition it again. And then I have to do some, so one of the hard things is speed matching, and we'll talk about that in a second. The other hard thing is this, getting it close and dealing with when you need to switch between different mechanisms of navigating. And the last one is turns. Turns are quite difficult because if the lead vehicle turns, you don't really know about it in time. And so we'll see in a second, I've got some turns. It's not just a straight mission. And what it will do is the lead vehicle will turn and the follow vehicle will start dropping points to follow the other vehicle around the turn until the turn's over, and then it might switch into heading mode again. So I think this is a little longer in a straight line than I was hoping for with everybody watching me, but it will turn in a second, and then you'll see how that works. I just want to show you the turn, then I'll kick on to have a quick look at some of the code that I wrote to make that work. But it works really well. And as you can see, in the air, now here we go, here's the turn coming, and the lead vehicle is going to turn. It's just a slight turn here. So it didn't, there's a kind of a threshold that I put in about how steep a turn it is before it decides it has to do a real turn. So it did a little bit of a turn. It lost track. It started dropping points again until it catches up again, and now it switched back into heading mode again. And then the same thing, and then I really do want to get a real turn. I think this is it coming up here. So here we do a real turn. So now it doesn't realize till too late that the other vehicle's turned and loses track, and it has to catch up. And now you'll see that the airspeed of this follow vehicle starts ramping up and it's dropping points to try and follow the other vehicle. And the behavior has to be different depending on whether you're on the outside of the turn or on the inside of the turn with the following vehicle. Let's go back to this presentation. So this is the core of the navigation code, and I don't really need to go into it in a lot of detail, just to say that there's a whole bunch of logic around if I'm close to the other vehicle, if I'm doing a turn, if I'm doing a tight turn, in other words, I'm on the inside of the turn or on the outside of the turn. So several different circumstances, I figured out that I need to be doing heading mode. I'm flying to try and track the path of the other vehicle. And the other one is target location. So that's dropping points. And both of those are using the MAVLink command int interface that dropped into the Lua API bindings. So it's been really useful to have that. The fact that you can call pretty much anything that there's a command int function from MAVLink from Lua means, and I use those for this, but this, I did have to make a couple changes in the low-level code because I'm running this at about 10 hertz, about 10 times a second. I want to update the location. If I run it lower, then I do things like I overshoot massively because a plane can travel, an awful long way in a second or so. The default is that it will ignore these messages if they come in quicker than every 3 seconds, and that's a bit long. So I'm proposing to put in a parameter that sets the limit to how quickly these messages can be interpreted. And I want to be able to run it at about 10 hertz to get it to work well. Getting the speed to match was actually the biggest challenge up front. No, not up front. It was the first thing I thought I'd solved and turned out to be the last thing that I really did solve. I went through multiple iterations of the logic of this thing, trying to figure out how to get the speed of the follow vehicle to match this, correctly match, usefully match the speed of the target vehicle. It seems pretty straightforward, but the problem is, of course, that, you know, planes don't have brakes fundamentally. And so if you have a following vehicle following the target and it catches up, you want it to slow down enough so that then it matches speed by the time it's right there. Because if you keep going fast enough to catch up, you'll probably end up going back beyond it. And that was happening an awful lot. And I put all kinds of complicated logic in until I talked to a friend of mine called Justin, who is an engineer by trade. And he basically said to me, you know what, you should be using a PID controller. And I thought, well, that's too hard and I don't really understand them. But sure, okay, fine. If you say it's easy, again, aerobatics Lewis script from Tridge. He had a PI controller in for doing the aerobatics. I took that, dropped it in, created a module so that it can be just included, and that'll be part of my PR. Actually, I added a D as well. So there's a PID controller module that you can just require into a Lewis script that will create a PID controller. And then the other part of the problem is the discussion around error. And I've learned enough about PID controllers, as someone explained earlier today, that it's the error that the PID controller is managing for you. I did something interesting, and I'm not really sure if you're supposed to do this, but it works. And that is, if you can look at the first one, I have one PID controller on the differential velocity between the two vehicles. That's what DV is for. But the error that I use is not a velocity error, it's a distance error. So I use the distance between the target vehicle, or the follow vehicle, and that point that I'm trying to hit with the offsets. And I use that as my error, but then I have the PID controller return me a velocity. So the first parameter being passed in is the differential velocity. My error is a distance. It actually works. It returns to me a differential velocity that I then feed into a second PID controller right away on one line below. And that one gives me a target vehicle airspeed based on using that differential velocity as an error. And so by cascading those two PID controllers on top of each other, it was a bit like Justin told me, when a PID controller works, it will just magically work. And it really did. I deleted about 20 or 30 lines of code that was doing all kinds of complicated things. And these 2 lines of code, that's what you saw flying. And it really quite nicely matches the speed now. It speeds up enough to get close to the vehicle, which is where my differential distance is the error, means that I don't overshoot. And then it matches the speed of the target vehicle, which is what the second PID controller is doing to give me, so that when they're beside each other, they will stay beside each other. And I do want to quickly show that one because it's quite nice. This is the last video I think that I have. Oh, no, I decided not to show you that one for some reason, but, and I won't change my presentation, but so that was, but since I've got it open, I'm going to show this too. This is a turn video. So we're just about to talk about the turning, and I think I might as well show you that one. And this is from the ground. I just love how cleanly that follow vehicle follows the other plane around. Sort of magical in a way. Sorry, I really like it. Okay. Let's go back to the presentation. All right. And that we talked about that. We talked about the two different guided commands that I used for doing the change heading and the change speed and change altitude and do reposition. Effectively, guided heading mode or guided heading mode in ArduPilot really has two sub modes. One is location and one is heading, and it can work either way. And I switch between them to make it work. Oh yeah, and attitude for turns. So that's where this video leads into this, and that's the last piece that I really wanted to talk about in terms of major challenges that I had to address, and then things that I believe I've solved. And like I've tested this and flown it multiple times, not just that one flight that you saw, and it really does work. But figuring out when the lead vehicle is turning is hard. If you just use the global position int, which is what feeds into the AP follow library. And I might just diverge a little to mention that most of what the Lua script is doing is relying on the core of what's already in ArduPilot. You know, a bit like Nathaniel's message earlier, ArduPilot has a lot of stuff. It's already there and it's great and it's magic, ArduPilot magic, it works. And so what I do, when I looked at what Copter did, I found out that there's already a AP follow library in Plane, and there were a bunch of bindings already there. So I didn't really have to do a lot. I just had to figure out what the hell it was doing, because it wasn't really that obvious, and there's some weird and funny names for the APIs and stuff. So I had to do a lot of reading of the C code, but I didn't end up having to change an awful lot to make it work. And what it effectively does is it gets a global position int message in MAVLink, does some math, figures out what the target vehicle is doing, figures out where the follow vehicle needs to be, and then throws that over the wall and says, okay, you figure out what you want to do with it. And that's where ArduCopter has C code that figures out what you want to do with it. And now I've written a Lua script that figures out how to make the plane do something useful with that information. And what it was giving me was it was giving me the location of the target vehicle, and it was giving me the heading. But by the time the target vehicle's heading has started to turn around a turn, the follow vehicle's already massively overshot. And so I added pulling the attitude of the target vehicle. And so from the attitude of the target vehicle, I can find out its roll and its speed of roll. And therefore and then I project that ahead a couple of seconds so that I can tell, and I mean, it probably needs tuning a little bit, but right now I use about 2 seconds, and I can tell that the target vehicle is going to turn. And based on some complicated maths, well, really high school maths that I can barely remember, mostly trigonometry, but I harvested the code, and thanks Bob for your help with this, out of Mission Planner to calculate the turning radius from the roll and roll speed of the target vehicle. And based on the turning radius, then I calculate what the heading is going to be of the target vehicle 2 seconds ahead. And then I tell the target vehicle to start heading for that heading anyway, even if the other vehicle hasn't turned yet. So that is, that's how that works. And, oh yeah, I've got this other one. Should I do that one? I'm going to say no, unless someone asks about it. But what I found was that I was also targeting a gimbal camera in one of my test vehicles to point the gimbal camera at the target plane as it was flying around. I was finding it was very glitchy. It would point at the target plane, and then it would suddenly glitch back and all the time. And I finally figured out that it was telemetry. And so what's actually going on is that if it's not getting telemetry updates quickly enough, the camera will keep pointing where the plane was for a while, and then it'll figure out it moved, and it'll suddenly jump. And it was good that I did that, because that was a real cue to the fact that I wasn't really getting good enough telemetry updates to the follow part. And so it's one of the things that I've only just done, which is that I've started to increase the telemetry rate of the messages, global position and attitude coming from the target vehicle into the follow vehicle. And also there's some very cool work that Peter Barker and Leonard Hall have been doing with follow that I'm really looking forward to getting to when I can start to use it, because it's going to do kinematic interpolation. So it should be able to smooth out those gaps really in the information that I'm getting from the target vehicle and give me a predicted smooth path so that I can follow effectively the smooth path. Again, a bit like before, ArduPilot has magical things that happen inside, and if you use those, you can do even more magical things on top of it. And so I think it'll make significant improvements both to that and also I think to the ability of a gimbal camera, which I'm going to be using Frank-Your CE8 mini camera. I plan to mount on the follow plane and then have the gimbal camera tracking the follow vehicle as it flies around. I think it'll be very, very cool. I did want to mention there's this weird offset problem. I already talked to Tridge about it. I'm not really sure what's up with it, but and maybe the kinematic interpolation will fix it. For some reason, the offset that I get from the target vehicle isn't quite right, and I end up having to apply like a fudge factor to it to get it correct. I parameterize most of the things that happen. Okay. I think I've talked about most of these. I just want to talk about some lessons that I learned here quickly. Text can fly the plane. Text is amazing. A well-tuned text or a really nice text tune of a vehicle means that you don't have to think. You can just tell the plane to fly and it will fly. And so that's where it was really easy in the Lua script to just say, go here, and the plane will deal with how to get there. And it really works. So some people have a tendency when they think about this thing to think, oh, I have to control the throttle, I have to control the ailerons, the elevator, whatever. You usually don't for this anyway, for this kind of application. You tell the plane what to do, it figures out how, and it really does work. AP follow does all the basics. Unfortunately, you really do have to read the C code to figure out what's going on. The copious ArduPilot wiki documentation that I've tried to help improve, working with Henry Wurzburg, who does an amazing job, and a lot of you have also helped here. But I think in this case it probably needs some more work, and I might try to help with that. PID controllers are magic, just magic. And they can do things that you really don't expect. When I learned that it did this, I'm already starting to think, is there a way that I can use them for the turning as well? And yeah, oh, telemetry rates really matter. And I kind of assumed that I'll just use what's there as the default and fix it if it's a problem, but I should have thought more about it. And now that I know how important they are, I'm going to have to start doing things like Tridge suggested, is get the follow plane to request the telemetry, global position and attitude, and anything that I specifically want. And I'm guessing, I think at about 20 Hertz probably. And then of course, testing. Like any software development exercise, testing is everything. It's not done till it's tested. And in ArduPilot terms, CIDL testing is amazing and gets you to a certain level. But then you really do have to take your heart in your hand and throw a plane in the air and see what happens. And I think in some ways I feel lucky, and in some ways I think it reflects what I've learned, and also a lot of the good work of almost every one of you here. Touch wood, I haven't crashed any planes doing the follow yet. And I do expect, I expected that I would by now, and I probably will, but it's testing. I was very cautious about doing it, but it works and it's great. I'm not going to talk about this diagram. It helped me to think about things, but also, but what I just do want to say is And thank you very much. Questions?
One or two questions.
Hey, Tim. So quick question on, I know you talked about the SICK radio, but can you describe a little bit more your telemetry setup? Is there multiple networks or a mesh? And then does your script handle if the follow plane doesn't get telemetry for some threshold, what does it do?
Yeah. So the SIK telemetry radios is a simple point-to-point between the two planes. Originally, I did set it up going through the ground station. The microphone can probably move while you, yeah. I did set it up going through the ground station, and the latency was just killed it. I have a separate radio link for control of the planes. I'm using Express LRS, and then I have the point-to-point SIK telemetry radio between the two. The Holybro radios, Vincent, they seem to be doing mesh, because I can also connect to the ground station when I'm on the ground to two planes, and I haven't done anything special and it worked. What I was expecting though, and the question that if you're not going to ask it, many people have asked me this, is, well, can you do 3 planes or 4 planes or more? And the answer should be, I haven't tested it, but absolutely no reason why not, as long as you can get the telemetry. The vehicles have to have a different SysID this MAV, but technically you could have 2 planes following the lead plane and then 2 more planes following each of those planes, and you're pretty much limited by the 8-bit 255 limit on those MAVLink SysID, or the bandwidth of your telemetry links, and then you might have to design a more sophisticated way of doing it. Or what I plan to do, and I was talking to someone else here today thinking about this, is use LTE with a basically internet connectivity. I'm thinking between the planes might be a good way to do it. Yeah, but I don't know. Does that answer the question? Oh, yeah. So I put in some timeouts, really. There's a couple of timeouts. One is that if it fails to get a message from the other vehicle in a certain number of seconds, which is a parameter, and I defaulted to 5, then it will flip into heading mode and keep heading in the same direction. And then if it, at a longer interval, which I defaulted to 20 seconds, I think, then it's again, a configurable, you can actually say, configure what mode you want to switch it into. So there's a variable of fail mode, ZPF fail mode. Oh, and I want to mention, I use this standard for my scripts now, where I put Z in front of anything that's scripting. So I have ZPF, Z plane follow, fail mode, and I default that to RTL, but you could specify whatever you like.
Thank you so much for a very interesting presentation. We've done with the sea rescue, we tried to do the same, but to follow rescue vessels, so AIS targets.
Oh yeah.
But there we have a problem with the telemetry, basically,
Yes.
from the vessel, because it's not as fast. But one very specific question is with the heading mode. We tried to do like an FPV mode over with our GCS, but we didn't find the heading or guided heading mode. Is that something you've implemented, or?
No, it's just there is a guided heading. It's the MAVLink message. That's maybe where it's coming from. It's actually underneath in the covers. Guided mode has a guided heading type, and it can take a heading from and I'm not sure how you send it to it except through an API or from Lua. But I switched to using the new MAVLink command interface. So with that, you can say guided change heading, and the MAVLink guided change heading command lets you set the heading in degrees that you want the plane to fly. And really all you need to do is change what I said earlier, is allow it to get more frequent updates, because by default, if you send a guided change heading command right now, and then you send another one, it'll say, well, you have to wait 3 seconds before you're allowed to send me another one. And that's really not fast enough. But otherwise, that's how you do it. And that's how I did it.
Okay. Thank you very much.
No problem. All right, I think, oh, there's one at the back. Oh, yeah, I want to do Peter. Please let me do Peter.
So really, this is just scope creep in the guise of a question. Yeah, you just mentioned the problems you were having with the mount being jerky.
Yes.
And that's kind of just a design deficiency in the way mount does SysID targeting. The fact that it just, when a message comes in, it just sets an angle. And oddly enough, the target's moving.
Yep.
So yeah, if we switch that to some form of rate control rather than angle control, things would probably work a lot better. We have the information, I believe, in the follow library. So
Okay, thank you. Good. All right then. All right. Arigato gozaimasu.
Let me get my papers as well. Yep. Already sharing. Okay. So do we have the person? You should hopefully have your presentation there somewhere. It's oh, this one. Okay. No, not on Mac. Where it is? Maybe just minimize that thing. Yeah, drag it somewhere. Probably one of these. 40 slides, eh? That's gonna be a little. No, they're just the transitions. I'm happy with that. It's fine. Yeah. Yeah. Okay.
Hello, people. My name is George. The last name is Zogopoulos. I call myself a controls engineer. And for the last few months, I've been a new member of the ArduPilot developer team. I work for myself, and you can already tell I'm doing this wrong. I don't have any company logos, no contact details, nothing. This presentation is not going to be very long, so maybe I could start with some dawdling. So in my previous life, I was a PhD student and researcher and was writing and presenting papers for IEEE conferences, cutting edge research, all of that fancy stuff. But so a few months ago, when I learned about this conference, I said, okay, I've kind of missed this. Let's try to do this again. I thought, yeah, let's not get too rusty on writing papers. Set a few goals for myself. Keep the IEEE conference vibes streak live. Maybe take advantage of all those long hours I spent on graduate courses and put them to good work and try to contribute maybe some proofs, some formal proofs for the ArduPilot controllers. Both you and me are in for disappointment. So this is not by any means a peer-reviewed paper. Nope. I wrote this is not a EEE conference as a bad thing 2 weeks ago, but in hindsight, no, it's actually better. So that's an upside. I realized I don't remember nearly half, maybe quarter as much from what I learned like all those years ago. And finally, yeah, formal proofs for real vehicle controllers. You're not going to find those exactly in this presentation. So let's revise our goals and let's try instead to have some fun. And remember that research is hard on your body. Try to take breaks when you plan to do long hours on a chair. All right, so let's get into the main course. And feel free to ask questions whenever, it's fine. We heard today and yesterday about a lot of nice tooling we are developing for linear systems We have FFTs, we have Bode diagrams. We now heard today about more tools to tune our linear controllers. PID is a linear controller, by the way, and all that good stuff. There are some parts of our system that are not linear, though. And Nathaniel did a good hint at this. That trike, it was not behaving linearly exactly. So when does this linear assumption break down? It's either when the system is nonlinear, and I have here an example of the altitude rate as a function of velocity and pitch angle. And the other case when the linear assumption breaks down is when your controller is nonlinear. And you know what is fitting both of these? TEX. So TEX as a system model does not assume a linear plant, and its inner workings are not linear. So we have ourselves a nonlinear system, and our linear tools don't work on this, right? So we have a mid 20th century control problem here. And who do you turn to when you have one of these? To like 19th century Russian mathematicians most of the time. So the go-to guy for today is Alexander Lyapunov. He was born in 1857, so it's not exactly cutting-edge research we're doing here. To an astronomer dad, nice. And he was a student of Chebyshev, for those who care about those kind of things. He is considered the father of stability theory in dynamic systems. But yeah, I don't speak Russian. So who do you turn to explain these to you? And the go-to bibliography for today is an Egyptian American, Hassan Khalil, who wrote, and this guy is still alive. Retired though, but still alive. And he's written this marvelous book, who is like the go-to textbook for all things nonlinear. There are literally thousands of publications in conferences and journals and monographs about how do you tackle and analyze nonlinear systems, but specifically for the ArduPilot controllers, I couldn't find any. If you have any references, please point me to them, and that would be really lovely. But that means that I kind of started from scratch. And that said, let's kind of revise our goals then. So for today, what I want to show is whether TEX closes a stable loop. We know from the outcome that it does, and try to uncover any hints on tuning TEX based on what we're going to say today. So as with any control problem, we'd start with our model. For this, we're going to need only our longitudinal airplane dynamics. We're going to assume a really good pitch tracking for today. We're going to use a very simplified thruster model. It's that Ft times delta T, like constant force modulated with our throttle signal. And a drag model that is not the simplest one. It's just complicated to be useful, perhaps. We could do, we could do simpler, we could do more complicated. It's like midway there. And we are going to limit ourselves to a regulation problem. Basically, how do you take a constant altitude and speed reference set point and try to track that? We're not going to go through climbs and dives and these kinds of transitions. On the controller side, the text.cpp file is around 700 lines of code, maybe more. So I had to do an interpretation to distill everything into simpler equations. And this is why, Bill, I asked you how easy was it for you for the PID counterparts. So I started drawing my own like diagrams on Draw.io, and this is an example of how you get the inputs to text and construct the velocity set points. And it got out of hand pretty quickly. Yeah. So you will need to trust me on this for today that I did a good job like keeping the essentials of text. Yeah, like I said, it's not peer reviewed. But for today's analysis, we also need to come up with a so-called autonomous system. An autonomous system is a dynamic system that doesn't have any input. It has a state, and that state evolves according to those dynamics. And to do that, we take our plant. That plant does have some inputs. We substitute for the controller equations through that closed loop. And the autonomous system is the outside view of that pair. Yeah. That doesn't look very manageable either. But still, it is something we can grab onto and see where it leads us. The next thing that we need to do is to find the equilibrium points of that autonomous system, basically see where it wants to settle. These are points basically where if you place the system states there, the system will not move. There are stable points, let's say that. Stable is not the best word. There are points more accurately that where the derivatives don't change. Sorry, they stay zero. Some of those points can be stable. Some of those can be unstable. In this case, we'll see that it is a stable point. And indeed, when we try to solve for zero derivatives, we get the velocity and altitude set points, which is a good thing. It means that the text can stabilize that system on the desired set points. And we can see the bottom two integrator states that they need to wind up to the expected values to keep that system stuck there. The next thing that we need to do to apply our theory is to translate the state coordinates around zero. You noticed earlier that the altitude and the velocity are not zero. We don't want to fly our airplane at zero altitude, and it can't fly at zero airspeed, but really we need to basically substitute the arbitrary altitude and velocity set points to a trim point. Substitute that trim point from our states, and yeah, we have a new frame of reference where the zero is our desired state. Most stability analyses assume that the desired stability is at the origin, but that's fine. It doesn't break anything. It doesn't mean that it's not applicable. It works just fine. It's just a mathematical trick that we do to generalize our approach. And this is where linear analysis needs to come and assist us a bit to show that this trim point is actually stable. So we go through the usual steps of linearizing the nonlinear system on the trim point and try to get a stability assessment. And this is basically what you see here. It's a state transition matrix on the top. It has the text parameters left in as variables. I substituted the rest of the variables, masses, drags, etc., with numbers. Still, it's kind of hard to tell if that top matrix is a stable system. So I went ahead for this example and substituted with actual numbers, of which you can get some eigenvalues. You can see that all the real parts are negative, so we are happy. This system is going to be a stable one. This trim point is stable. So we can start now our nonlinear analysis knowing that this trim point, yeah, eventually it's stable. We can try to see how it behaves. And at this point, we can do sort of an intermission and talk about how does the system actually evolve around that stable point. And these are some trajectories, essentially, of a two-state system, looking at it from top down. You can think that horizontally, that's altitude, vertically, it's speed, for example. And the arrows on the line show what happens to the system, how it evolves if you let it and you start it from an arbitrary point on that plane. For a stable origin, you see that from wherever you leave it on that plane, it will eventually draw a trajectory that will lead it at zero and stay at zero. If it was a saddle point, so-called saddle point, it would converge on one state, on the vertical state, but it would diverge on the other horizontal state. Or it could be a focus point describing circles around that two-state system, eventually ending up at the origin, but through some oscillation. Or it could be a center, basically circling around that center, but never actually minimizing the error to zero. And there are some more other cases of trim points that we won't get to now. This is basically a so-called phase portrait where nonlinear systems are concerned. And this captures, like I said before, the trajectory of the system via propagation. To draw such a phase portrait on a diagram, you need numerical values essentially. So you do need to have some sort of an idea of a system at hand and replace variables with numbers. But it is also expected to reflect what the linear analysis pointed, at least locally. If your linear analysis said that the origin, specifically the origin, is stable, you would expect the nonlinear phase portrait to behave quasi-stably in a neighborhood around the origin. This is pretty in appearance to what we saw before as a focus point, but a phase portrait of a nonlinear system doesn't have to be. Like it could be like this. And this is from a book example of a tunnel diode circuit. It can be completely nonlinear, very weird. Thankfully, we're not at that case. And at this point, we can apply the core of today's analysis. This is the so-called Lyapunov's theorem. And it is a sufficient condition that proves that the autonomous system that we have at hand is actually stable in the Lyapunov sense. That's a technical term. The proof comes down to finding a function, an arbitrary function v of the state that needs to be positive everywhere on the domain that we care about investigating. And it needs to be, its derivative needs to be negative everywhere on the domain that we care to investigate. And if those two things happen, and we find V that satisfies those two conditions, then we can guarantee that our autonomous system is stable. So a naive attempt of Lyapunov function, before I say that, let's say that typically the Lyapunov function V is a representation, is a mirror of the energy of the system. The energy needs to be positive at all times. This is why it needs to be positive as a function. And if its derivative is negative everywhere or zero at the origin, it means that the energy of the system gradually and continuously diminishes so that the system degrades and settles on the origin. So if we use just the sum of the squares of every state of the system as an energy function, that's the most naive approach we can come up with, it yields pretty long expressions like the one at the bottom. Like you can't draw any conclusion from that. Like, is this always negative? Who knows? But it's kind of important to get a good insight on that Lyapunov function, because it also helps you draw conclusions about the conditions for stability for the system. So if I could understand how all of the variables on that derivative work together, or what relation they need to have with each other so that the whole thing is negative, I could draw conclusions about, okay, if, for example, it says that the arbitrary thought, the product of the text pitch gain, pitch damping gain, and the next period needs to be less than 12, then okay, this is progress. But yeah, this expression is really unwieldy. So you can't solve an expression, just calculate it, but you do lose like the flexibility. The moment you replace with numbers, you can get your analysis all the way to the end, but you have lost a lot of insight. In this case, what I tried to do was to keep a two-dimensional system and keep two variables free, basically. The text time constant on the one axis and the text pitch damp gain on the other axis. And what I did was that I evaluated the Lyapunov function derivative all over the domain of a few meters per second up and down on the velocity axis and a few meters up and down on the altitude axis, and plotted the maximum of that Lyapunov derivative. And you can see how for some values of the time constant and some values of the damping constant, you get positive values. Like I'm getting them, I'm plotting the max of the max. So along that whole phase portrait, I take the maximum value basically. And if that's positive, and for some cases it is, like we see here, it means that our system oscillates or escapes basically and drives away from the origin. Whereas for some values of the time constant of the pitch damping, it is negative everywhere. The maximum value is negative, so everything is definitely negative. And this means that that system in comparison is more stable. It gets to the origin for sure, and probably faster. So what results can we draw from this? Yes, we have just shown that under some numerical values, text is stable. It closes a stable loop, and that's a good initial verification for the proposed methodology. But as we saw, there are a lot of variables to move around and keep track of. The system was 6 or 7 variables, text is another 6 or 7. This amount of variables is like too much to lug around in a mathematical derivation. So we had to use some numerical values to process this analysis and progress. But we do gain insight, so we can transfer what we saw before, this image, and take the two edge cases, the one on the top left and one on the bottom right, those two combinations of parameters, draw these two phase portraits. And you can see that with the right values of text, the phase diagram of the system evolves more quickly towards the origin. Whereas with the left one, you have a lot of arrows escaping outside of the area of interest, and there's a diagonal line where the system doesn't strongly want to come back to the origin. So that's some good insight, and that is some pointer that maybe in the future I should try to see what is the relation between those two constants and why do they behave like this. I used a lot of numbers for this analysis. So for application on real systems, some parameter identification is necessary. And we saw today some pretty good efforts on doing parameter identification. But we didn't have such a complex model to begin with. And I think it would be not easy, but manageable to do some identification not so accurate, and it might be applicable to whole classes of vehicles. So you might have a set of model parameters that represent a sleek glider versus a really chubby biplane with some serious thrust, though. And the last takeaway from this talk is that all the math you just saw were done through SymPy. I didn't do it by hand at all. And that means that we can easily modify it, and you can go ahead to that repository, run for yourselves, and see how it works. So what's more to do after this? Of course, I need to keep on studying. I really did not have as much time as I thought before this presentation. I did less than half of what I was planning to do. So I need to go back and hit the books, study more relevant applications. There are a lot of theorems that allow you to simplify your analysis and make you less reliant on chugging and lugging around all of those variables that you can substitute with simpler functions a lot. And another good pointer is the passivity theory that lets you get a modular system, prove that all of your modules of that system are passive. And if they are passive, then the combination of them is going to be passive as well. And this is perhaps for complex systems, a more manageable way to prove stability. And if you indulge me this far, sincere thank you. And you can ask your questions if you have any, or remarks, or we can just speed along to the next presentation. We're way behind schedule. Nathaniel was first on the line.
Thank you. Really cool talk. I think we kind of have the same way of thinking about this stuff. It's like, how do you apply the math in useful ways to answer problems on stability and control? And yeah, so the main thing I wanted to ask you, it's a bit more heady. It was, what would you say is the most promising direction you've seen for answering how you can generally address nonlinear stability? The reason I ask is because, as far as I know, it's an open problem. Like, that's part of why we don't know how to do it. No one's really got a general framework like a linear system to say it's stable and here's how I know.
I think there are enough decades of research on nonlinear systems, controls, and stability that for us as an ArduPilot community, it's a matter of getting enough experience to identify and connect the right piece of research to our systems. We need to identify the category, the class of the systems that we are running to the correct research and how, like, full-time researchers and professors solved those control problems. So the general nonlinear stability is, yes, an open problem, but the historical research has come up with a lot of individual classes of systems where proofs exist, and we need to find them.
Yeah, and then just to follow on, you mentioned at the start how you had plans when you started out to publish and whatnot. I just think that's healing after you finish the work at the start, right? Like it's a natural part of the process.
I had that moment 1 week ago when I left home because I didn't bring a laptop with me. So this is why I have that old ArduPilot logo, because Randy dropped this one day after I left home.
Awesome. Okay, thank you.
Thanks for the question. Oh, and of course, thanks to Tim for lending me his laptop.
So Thomas has kindly agreed to move his talk till tomorrow. So we just have one more to go, which is Peter Van Goor from ANU, and he's going to be talking about a DCM replacement. He is remote from Australia, so just give us a couple of minutes.
So yeah, this is going to be our first remote talk. And so when you're ready, Peter, hopefully you can hear us now. So
I can hear you. Can you hear me?
Yes, we can hear you, Peter.
Wonderful.
So now can you screen share, Peter?
I think so.
Okay, try and share your screen now. So
There we go.
I've worked with Peter for a number of years at the Australian National University in Canberra. Peter's currently in the Netherlands, and he's joining us from the Netherlands today. This is our first attempted remote talk at this conference, so we'll just have to see how it goes. All right, over to you, Peter.
Thanks a lot. Yeah, hi everyone. I hope you can hear me well and see me well. Yeah, so what I'd like to talk about is the CINS, as we call it, the Complementary Inertial Navigation System. As Randy mentioned, it's kind of a DCM replacement, and it's kind of something else, but I'll explain. And one other thing I should add is that this is really sort of an update to last year's talk, where we introduced CINS for the first time at an ArduPilot Developer Conference. Okay, so what is CINS? It's a new geometry-based approach to inertial navigation, which this year at least uses the inertial measurement units, so the gyros and accelerometers. It uses GPS measurements, both position and velocity, and it uses magnetometer measurements. And what's special about CINS is that the mathematics on which it's based are totally different from the existing EKF. So while the EKF is based on probability and stochastic processes, CINS is based on geometry principles. And the nice thing about this big difference in the mathematics is that we expect to see totally different failure modes as well. So of course, every filter can fail somehow, but we should hopefully see that they fail in very different situations. In theory, thanks to the derivation, the way we've done it, CINS should provide global stability and convergence properties. Of course, in practice, there's still a lot of assumptions around that the measurements are somehow nice. And yeah, since last year, we've developed CINS from being a nice idea with some very initial results into an actual viable alternative state estimator that's currently on a pull request into the main branch of ArduPilot, I think. So what are the goals of CINS? CINS, as mentioned, is similar to the DCM in the sense that they're both based on geometry and they both provide this global stability and convergence. However, unlike the DCM, which only provides attitude estimates, CINS provides a full navigation state. So like the EKF, it provides position, velocity, attitude. It even provides biases for the gyroscope and accelerometer now. At the moment, our aim is to gradually replace the DCM with CINS as a fallback for the EKF. But long term, what I'd like to achieve with this is to provide a full-featured alternative state estimator to the EKF, so that you, depending on the sort of behavior you'd like to see from your state estimator, you can choose which one suits your need better. Okay, and where are we at this year? So, like I said, you can fly CINS today if you want. You just have to check out the relevant branch from Tridge's fork of the ArduPilot, and then add this flag, enable CINS to your WAF configure command. And there you go. The rest is as usual, and then you should be able to fly CINS. So far, the tuning that we've set as a default has worked well for our tests. We've tested on both copters and a plane, and the performance is reasonably similar to EKF3, although we're not able to use all the same sensors that EKF3 uses. Notably missing is the barometer. So I want to give a bit of an overview of the different features of CINS, and I'll explain some of these in a little bit more detail. Firstly, there's the stability properties. So unlike the EKF, which is only what we call locally stable, meaning it'll recover as long as the error is small enough, CINS should recover from any error, no matter how large. The second feature is GPS delay. So we derived some new mathematics to handle GPS delays in a natural state-independent way. We've added some sense of modularity. Now, this is what I mean by this is that we're able to use magnetometer and GPS velocity, but you can use also only GPS position, and you can actually estimate the full navigation state using only GPS position. So you don't have to rely on having a magnetometer or GPS velocity available, although you can use them, and of course they should, in general, improve the estimate. Very recently, we added a rough indication of filter health by using a low-pass variance filter. And one significant change for practical purposes from last year is that we actually implemented the tuning in a way that you can set the tuning parameters directly through MAV proxy. You can change them mid-flight if you want, but do so at your own risk. So I want to talk really quickly about these different features. We have GPS delay and smoothing. So as I mentioned, we developed some new mathematics to handle the GPS delays. And what's really important about this is that the way we handle them is totally independent of the current estimator's state. It only depends on the incoming IMU measurements. And this is a really important property to ensure the robustness of the filter. Moreover, with this mathematics, aside from handling the inherent delay in GPS measurements, so you always have something like 100 to 200 milliseconds of delay, we can also use it to smooth out the GPS measurements. So what we do is when we get a GPS measurement, instead of doing a big jump to our estimate at that time, we actually do a little jump and then keep doing little jumps until we receive the next GPS measurement. But of course, as you progress in time, the GPS measurement becomes more and more delayed. But because of the mathematics we have to handle this delay, that's okay. So what are the results? Basically, one, the fact that there is GPS delay doesn't really deteriorate performance. And the second thing is that because the state updates are smooth, because of this smoothing, this gradual delay of the GPS measurement, we end up with a much smoother trajectory estimate rather than one that jumps at the rate of the GPS. Okay, I mentioned modularity. I've got some simulation results on the slide here. So even with only measuring the GPS position, in addition to the IMU inputs, you always need the gyroscope and accelerometer. But even if you only have GPS position, we're able to get global convergence, so converging from 179 degrees of roll in the estimator error. Of course, if you add other sensors, then the estimates converge more quickly. What the graph shows is 4 different versions of the estimator, SP being position only, PV being position velocity, PM being position magnetometer, PVM position velocity magnetometer, compared to the true trajectory. Now, these are simulation results. They're not practical flight results, of course. I would be hesitant to turn on the estimator with 179 degrees of roll in practice. But still, you can see that even with only the position measurement, if you look at the red dotted line, it does actually converge the whole filter state. Okay, in terms of tuning, we have 18 gains to tune. Most of them are relatively self-explanatory, I'd say. I mean, there's the gain for GPS position, the gain for GPS velocity, the gain for the magnetometer, etc. One important thing is that these gains are not really like the noise covariances that you see in an EKF. So in an EKF, you'd have to work out somehow the stochastic properties of your sensors. These gains that we've got are much more like traditional PID control gains. So there's somehow some sense of a proportional gain, a derivative gain. Yeah, so it's a matter of tuning them. It's not a matter of working out stochastics of your system. And as I mentioned, you can set these now directly from the parameter editor in MAVProxy if you're flying. Although, yeah, of course, be careful. Okay, so to summarize, I thought I'd put up some tables. Here's the first one, comparing to where we were at the developer conference last year to where we are this year at the developer conference. I've highlighted the new additions. So already last year, we were estimating all the states. We had gyroscope and accelerometer inputs. We had GPS position outputs. This year, we've added compatibility with GPS delay. We've added GPS velocity, which can also be delayed, by the way. And we've added the compass. We've also added new states, the accelerometer and gyroscope biases, which turn out to be reasonably important for good flight behavior. And we've increased a little bit the number of gain states to be able to incorporate these. So the auxiliary states we've increased from 6 to 10, and the biases require separate gain states, a bit like covariance matrices, but a lot smaller. So we have 54 of those. We still manage to keep the same stability guarantees. We have our global asymptotic and local exponential stability. Let's compare that over to the DCM. So I'm just listing the 2024 version of CINS now. CINS provides a whole navigation state. DCM only provides attitude and gyroscope bias. Of course, it's not compatible with GPS velocity or position. But where they are similar is that they both provide the global asymptotic and local exponential stability. Compared to EKF3, we're looking a lot better now in terms of the comparison. We're both providing the same navigation states. We're using the same inputs. CINS is using GPS velocity, position, and compass, while EKF3 uses all of that, but it can also use airspeed. It can also use baro. I believe it can also use optical flow or VIO. So there are a lot of sensors that we haven't yet added to CINS. Unlike the EKF procedure, there's not a, if you tell me a model for the sensor, I can't just add it to CINS. I can't just linearize it and add it into the CINS filter. We actually have to derive some new mathematics to be able to do that in general. So this is why progress maybe is a little bit slower than it could be if we were doing an EKF style filter. Okay. In terms of additional states, we just have the accelerometer and gyroscope bias, while the EKF also has magnetic field biases and estimates the wind velocity. So there are a few more states in the EKF that are useful for flight that we don't support yet, but these are on the wish list. One big difference, though, is that all these nice features of the EKF do cost in terms of having a very large state covariance matrix. So it's a 24 by 24 matrix, which that's a lot of matrix entries compared to the number of states in CINS. And finally, the key benefit, I would say, of using CINS over EKF is that we do provide that global asymptotic local exponential stability, whereas the EKF only provides the local exponential stability. Okay, and just getting towards the end, I wanted to show off a few bits of experimental data. So this is from some flights we did. I think these were from the flights we did in May, testing out whether CINS could actually be used in closed loop for flying. What you can see here, what I want to point out is if you look in particular at the yellow, green, and black lines, the yellow and green lines are the EKF and CINS, while the black line is the AHR2, which is the DCM. And so what you can see is that CINS is much more consistent with the EKF than with the AHR2, despite, as I mentioned, being really based on these different mathematical principles. Okay, so this is roll and pitch. We also have yaw. And again, you see that, okay, there is a bit more of a difference here, but the output from CINS is still much closer to the EKF than the attitude heading reference system is at the moment, than from the DCM. In terms of, I also want to show off quickly velocity, north and east velocity. So what you can see here in particular, aside from that CINS and the EKF are reasonably consistent, what you can really clearly see is the delay in the velocity. So if you look at the dark green line, especially towards about 8:23:15, you can see that the velocity measurements are way ahead, way past the line from CINS or the line from the EKF. And this is what I mentioned about being able to handle that delay effectively. Okay, so I'll finish quickly. CINS has come a long way since last year. You can try it today. I hope you do try it, and would be really happy to receive any feedback. The performance of CINS is comparable to EKF3, but it doesn't support all the same sensors, so you should not expect necessarily to get exactly the same performance in all different situations. At the moment, my wish list for improvements includes supporting the barometer, supporting wind velocity or airspeed estimation, and taking advantage of the weather vane effect for fixed wings in particular. And aside from that, please get in touch and let me know what you'd like added as well. So any other features I'd be really interested in including. And I'll finish off by thanking all the people who've been a part of this project so far. So on the left, there's a picture from the day we spent flying CINS in May. And on the right are all the people who've been involved in developing CINS and the mathematical framework for this. Yeah, thanks a lot.
So questions now. We're okay? Yep. Great. So Rishab, got a question from Rishab?
Hey, Peter, great talk as usual, and nice to hear from you.
Hi, Rishab.
So a couple of questions from my side. First being, since you already have this working with ArduPilot, can I take my existing replay logs, which I usually have like a drive with like hundreds of replay logs at this point? Can I take that and compare your branch so that I know exactly what the differences are with the existing EKF data and yours?
I believe that should be possible. So we definitely do have it compatible with replay data. I don't know, this is my weakness, right? I'm much more an academic and a mathematician than I'm a software engineer. So
architecture-wise, it's built on top of.
It does work with existing replay logs.
Awesome.
Thanks,
So,
Rich.
so
Yeah.
in theory, we can already work with real life data from hundreds of vehicles already.
Absolutely.
That's
I
awesome.
believe so, yes. Yeah.
And my second question was, in the EKF, as long as we have a sensor model and states are observable, we can usually integrate them very, very easily. What is so different about this algorithm that it requires so much analysis for each sensor? And the follow-up to that would be, what is it in the sensor that, while we're picking out, how easy would it be to integrate it? Like, how do we know that?
The key feature that we've relied on to be able to integrate the sensors is that they're geometrically nice. I'll put it that way. So how to explain that? Basically, because with GPS position and velocity, you get the full position vector or the full velocity vector. And the same with magnetometer, you get the full vector. Compare this over to barometer, you only get one component of the position vector. You only get the height. And what the particular trick that we mostly rely on is if you change the reference frame with respect to which you express your system. So usually you think about the system expressed to an Earth surface fixed reference frame, an NED frame. But if you change this reference frame, then the effective position measurement you would expect to get changes as well. The point is, if you know what the GPS position and measurement is in one frame, then you know what it is in another frame. But if you only measure the barometer height, you don't necessarily know what it looks like in another frame because you don't know. You need the rest of the position states to be able to express that, and that's mathematically the reason that it's hard. In general, yeah, it's just not built on the same principles, so linearization doesn't work.
Right. I guess
I hope that's a decent answer to your question.
On that. Yeah, but thank you so much.
No, thank you.
So quick question on the the tuning side of things. You mentioned that it doesn't depend on the or is it correct when you said that it does not depend on the quality of the sensor or the stochastic quality of the sensor, how imprecise it is and stuff like that? What does it actually depend on, these biases and the tuning component of this algorithm? Like what would make it vary between, say, vehicles or platforms or sensors and stuff like that?
So maybe I didn't explain super well, right? But what I was trying to say is that these are not. You shouldn't read these gains as if they're covariances or inverse covariances or something.
Right.
Rather, they're like PID gains, right? So definitely, if you have a noisier system, you're going to need to retune the gains or maybe adjust them a bit. What I was trying to say as well is that the gains that we've put into as a default for now have worked across a number of systems,
right?
And have given decent performance.
Right.
You could probably improve the performance if you tune them more carefully, but then of course, if you have a noisier system, you might get worse results. This is, in general, the way that I would propose you think about PID, right, is that if you put the gain higher, your system will converge faster, but it'll be more sensitive to noise. If you put the gain lower, then it'll converge slower, but it'll be less sensitive to noise.
Right.
So this is very similar. Does that explain?
Yeah. What is the performance of this sort of estimation on, like, high dynamics situation, like, FPV flying and doing state estimation in those kind of system? Does it improve over EKF, or it's worse than EKF, or what
So our experiment, we haven't done that many experiments. What we did do, I believe Michelle flew an FPV drone at around 100 kilometers per hour. And that was a really nice test for CINS.
Right.
It managed to work and stay stable despite some very, very quick flights. Meanwhile, the EKF switched between IMUs because it was having problems. I don't think it broke, but you know, CINS is not built to switch IMUs at the moment. It just runs. And maybe Tridge or Michelle has a better memory than me.
Yeah, definitely would love to see those logs though. Yeah.
All of those logs are public.
Okay.
We have a public repository of replay logs, including all of those logs on that 5-inch freestyle quad.
Yeah.
Where Michelle was deliberately trying to break the state
Thanks.
estimators.
Yeah.
And you can replay those logs and play with them.
Very nice. Yeah. Thank you very much.
Thanks, Tridge.
Hoi, Peter. So, hello, George here. Is the GPS as a sensor in the minimum set of sensors required for this filter to work?
You require a GPS position. I mean, in general, we require at least a position measurement.
So CINS is different to the DCM in the sense that it can't just operate in an attitude only mode. It needs a position as well to converge.
Yeah, so it should be possible to.
We lost you there. Can you repeat?
Statics won't break from having only attitude measurements, but it won't. Numerically, it will break because it's expecting a position measurement.
Yeah.
So yeah, you do need a position measurement to run it at the moment. We could try and add a mode later if that's something people are interested in. If we did this, you would end up with just the original DCM, basically.
We have time for one last question.
Hey, Peter. Thanks for sharing this. So my question is just on your point you made about this in some way being better than EKF. I guess I just want to hear you speculate, like, isn't it apples to oranges, like a probabilistic model versus like a well-defined geometric model? Like, why would you say it's better? Is it just you have a better model, period?
No, look, I mean, I don't mean to say that one is strictly better than another. I think they'll both be better for different situations. Yeah, the key thing where you can say one is theoretically better is in terms of stability results. So CINS has a global stability result, the EKF doesn't. But okay, what does this mean in practice? That depends, right? It depends on your situation. It depends on how friendly your measurements are. Of course, one weakness in a sense is that we're not able to handle covariances directly. So the EKF, in theory at least, should be locally more optimal somehow than CINS. Whether this is true in practice is again questionable, right? So in the end, I'm sorry if I said one is better than the other. I shouldn't have.
I think I'm putting words in your mouth a bit. I guess maybe a more focused way to ask what I'm trying to ask is the Kalman filter lets you have some fudge factor, right, in your model. Do you have the same flexibility with a CINS approach?
Can you explain what you mean by fudge factor?
By fudge factor, if your model for the innovation is a little off, that's okay because you have sort of the probabilistic property to it. So I know I actually don't know what CINS is, like in terms of its lineage of where it's from, I guess. So could you just
Yeah, so I mean, CINS really is it's the grandchild of DCM, I guess. It's really built on the same principles, but applied. We had to develop some new Lie group theory and do a bunch of mathematics to get this to work. If anyone's interested, let me know, and I'm happy to send papers, right? But I didn't want to get into the mathematical details today. With all that said, you should expect similar performance to the DCM in a sense that, this, if you, the fudge factor you're talking about, it should work even if the measurements are not precise. How well that'll work depends on the gains that you've chosen. Does that answer your question?
Yeah, I think so. So the gains are what give you that model flexibility in CINS.
Yeah,
right?
yeah. So, and as a matter of fact, I mean, you can think of the EKF in the reverse way, right? That the covariances somehow dictate what the gains are in the filter.
Yeah.
Yeah. And so CINS is, yeah, it's just based on gains.
Okay. Thank you.
Thanks for your question.
All right. Well, thank you very much, Peter, for joining us, and delighted to have that. And I'm looking forward to more people trying out CINS on their own aircraft. And if you want help with the practical setup of CINS, I'd be delighted to help. We do have a CINS estimator thread on Discord if you want to join in there and discuss the practical side of setting up and running CINS on your aircraft. Thank you, Peter.
Yeah. Okay. All right. Well, thank you so much to all the presenters today. Obviously, there's a ton of work put into all those presentations. So one final round of applause to all of them. So next is the demonstration section of today. Perhaps I didn't explain it well enough, but it's a very short demonstration today. So yesterday was fewer presentations, more demonstrations. Today is more presentations, fewer demonstrations. So there's just actually going to be just one demonstration today out at a very scenic site called Kutani Dam. So it's a beautiful place. Crappy and Andy Piper are going to be doing a little FPV view, flight, which could be very nice. The downside it is a 40-minute drive. So this is optional. If you don't want to go, that's totally fine. We'll be showing a video of that flight at the banquet tonight. So if you don't want to go, you'll still see the video. What's that? I don't know exactly, but it's going to involve Trappy and Andy Piper FPVing at a dam, a very scenic view. We'll see what happens. So, sorry, I didn't give you a lot of time to decide, but I would like, if possible, we'd like to see numbers of who would like to get on the bus to go to the dam. Okay, can somebody count that? No, it's okay. We have lots of buses prepared.
50, something like that.
49 is the maximum. So somebody better count. Hold on. Wagata-san? Sorry, one per.